Hello there, and welcome to the Science for Sleepyheads. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to cosmic mysteries and deep thoughts rather than counting sheep. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if gravity itself has softened around you. Because tonight, we're not simply stargazing. We're venturing into the most mysterious objects in the universe: black holes, regions of space so dense that not even light can escape, places where time bends, where stars are torn apart, and where the rules of physics twist into something strange and beautiful. We'll drift gently from stellar mass black holes to supermassive giants lurking at the centers of galaxies, from event horizons to Hawking radiation, from gravitational waves to the question of what lies beyond the point of no return. You'll hear of objects that warp space-time itself, stars that spiral inward at impossible speeds, and phenomena that challenge everything we thought we knew about reality. Some of what you hear tonight may surprise you, or at the very least spark some curiosity as you drift off to sleep. And just before we begin, I'd love to know, where in the world are you watching from tonight? And how was your day? Drop a comment below. I always enjoy reading your comments. If these calm, curious explorations help you unwind or offer a peaceful way to end your day, consider liking and subscribing. I upload daily with new science topics to fall asleep to, so there's always something soothing waiting for you when you need it. It also helps others find their way here. Now, let's begin. The term black hole wasn't coined until 1967, even though the concept existed for decades earlier. Isn't it strange to think that we discovered something before we knew what to call it? For years, decades even, physicists knew that Einstein's equations predicted these impossible objects, places where gravity became so extreme that not even light could escape. But they didn't have a name that felt right. Some called them frozen stars, because from the outside, time itself appears to freeze at their surface. Others used the more clinical term gravitationally collapsed objects, which is accurate but doesn't quite capture the profound strangeness, does it? It wasn't until 1967 that physicist John Wheeler popularized the term black hole during a lecture. The name stuck immediately, perhaps because it captured something essential. Not just the darkness, but the emptiness, the void, the sense of something that exists by not existing in the usual way. Before we had the right words, we had the mathematics. Before we could name them, we could describe them. Sometimes I think that's how the universe works. It shows us its wonders first, and only later do we learn the language to speak about them properly. Black holes aren't actually holes at all, but rather regions of space where gravity is so strong that nothing can escape. The name is misleading in a way. When you hear hole, you might imagine a tunnel, a passageway, something you could theoretically travel through. But a black hole isn't a hole in space. It's more like a region where space itself has been pushed to its absolute limit. Think of it this way. Gravity is just the curvature of space-time, the way mass bends the fabric of the universe. Normally, this curvature is gentle. The Earth curves space just enough to keep you on the ground, to guide the moon in its orbit. The sun curves space enough to hold the planets in their elegant dance. But a black hole curves space so extremely so drastically that it curves right back on itself. It creates a pocket, a trap, a one-way street in the geometry of reality. Nothing can escape, not matter, not light, not even information, though we'll come to that mystery later. It's less like a hole you could fall through, and more like a trapdoor that only swings one way. Once you're in, there's no path back out, not because there's a barrier, but because every direction you could possibly move leads further in. Even the concept of out stops making sense. The boundary of a black hole is called the event horizon, the point of no return where escape velocity equals the speed of light, the event horizon. Even the name has a certain poetry to it. The horizon of events, the boundary beyond which things happen that we can never witness, never retrieve, never undo. It's not a physical surface. If you were approaching it, you wouldn't see a wall or feel a membrane. There's nothing solid there, no material boundary. Instead, it's an invisible threshold written into the geometry of space-time itself. Cross it, and your fate is sealed. Not because something happens to you at that instant, but because the structure of space itself offers no path back. Think about escape velocity for a moment. Here on Earth, if you want to leave the planet entirely, you need to travel about 11 kilometers per second. That's fast, but it's achievable. We've done it. For the Sun, escape velocity is higher, about 617 kilometers per second, still within the realm of physics we understand. But at a black hole's event horizon, escape velocity reaches the ultimate cosmic speed limit, the speed of light itself. And since nothing can travel faster than light, not matter, not energy, not information, nothing can escape. The universe has created a perfect trap, not through force, but through geometry. John Michell, an English clergyman, first theorized about dark stars in 1783, long before Einstein's general relativity. Sometimes I find it remarkable how ideas can arrive before their time, like seeds waiting in the ground for the right season. John Michell was a clergyman in 18th century England, but he was also a natural philosopher, someone who thought deeply about how the world worked. In 1783, he began to wonder, what if a star could be so massive, so dense, that its gravity was strong enough to trap even light? Using Newton's theory of gravity, which was the best understanding they had at the time, he calculated that such an object could exist. He called them dark stars. Of course, Michell's reasoning wasn't quite right. He was thinking of light as little particles with mass, affected by gravity, the way a thrown ball is pulled back to Earth. We know now that light has no mass, that it's affected by gravity through the curvature of space-time itself. But in a way, Michell was right about the conclusion, even if his path there was different from ours. The universe does contain these dark, invisible objects. He imagined them more than 2 centuries ago, working by candlelight, with nothing but mathematics and intuition. It makes you wonder what other truths are waiting to be discovered, what current ideas might be seeds that won't fully bloom for generations. Carl Schwarzschild solved Einstein's field equations in 1916 while serving in World War I, discovering the mathematical description of black holes. Here's something that always moves me. Carl Schwarzschild calculated the exact mathematical solution for black holes while serving on the Russian front during World War I. Einstein had published his theory of general relativity in late 1915, a revolution in how we understand gravity, space, and time. The equations were beautiful but notoriously difficult to solve. Einstein himself thought exact solutions might be impossible to find. But Schwarzschild, even while serving in the trenches, surrounded by the chaos and horror of war, worked on the mathematics in his spare moments. Within months, he had the solution. He found the exact description of how space-time curves around a spherical mass, and buried within that solution was the prediction of the event horizon, the boundary of no return. He sent his work to Einstein, who was astonished. Schwarzschild had found something profound, proof that Einstein's equations predicted objects even stranger than Einstein had imagined. Tragically, Schwarzschild died just a few months later from an illness contracted during the war. He was 42 years old, but his solution, the Schwarzschild metric, the Schwarzschild radius, lives on. In the midst of destruction, he found cosmic truth. In the darkness of war, he described the mathematics of darkness in space. Perhaps there's something fitting about that, though also deeply sad. Black holes come in different sizes, from stellar mass black holes to supermassive giants, millions of times heavier than our sun. The universe, it seems, likes to make black holes in different varieties. It's not a one-size-fits-all phenomenon. Some are relatively small, if you can call something with several times the sun's mass small, formed from the collapse of individual stars. We call these stellar mass black holes. Others are almost incomprehensibly massive. At the centers of galaxies, including our own, lurk supermassive black holes with millions or even billions of times the mass of our sun. Our galaxy's central black hole, which we'll talk more about later, weighs in at about 4 million solar masses. And yet, as massive as that sounds, it's actually modest compared to some. We've found black holes that exceed 60 billion solar masses. Objects so massive, they challenge our understanding of how they could have grown so large. What's beautiful, in a mathematical way, is that despite this enormous range in size, all black holes follow the same fundamental physics. The equations that describe a stellar mass black hole's event horizon work just as well for a supermassive one. It's just a matter of scale. Like the same song played at different octaves, the universe repeats its patterns from the small to the unimaginably large, following the same elegant rules written in the language of geometry. A stellar mass black hole typically forms when a star at least 20 times the mass of our sun collapses. Not every star becomes a black hole when it dies. In fact, most don't. Our own sun will never form a black hole. It doesn't have enough mass. When it exhausts its fuel billions of years from now, it will swell into a red giant, gently puff off its outer layers, and leave behind a small, dense core called a white dwarf. No drama, no collapse, just a quiet fade into cosmic twilight. Smaller stars than the sun have even gentler endings. They simply cool and dim over time, becoming stellar embers that will glow faintly for trillions of years. Stars with a bit more mass than the sun might explode as supernovae but leave behind neutron stars. Incredibly dense objects, but not quite dense enough to be black holes. To make a black hole, you need a massive star, typically at least 20 times the sun's mass, though the exact threshold depends on many factors. When such a star runs out of fuel, there's no gentle fade. The core collapses in less than a second, and if it's massive enough, nothing can stop it. Not electron pressure, not neutron pressure, not any force we know. It collapses past all barriers, through all resistance, until it becomes a point of infinite density. Or at least, that's what our equations tell us. We'll explore that mystery more as we go deeper into the night. The singularity at a black hole's center is a point where our current physics breaks down completely. At the very center of a black hole, hidden behind the event horizon, lies something we call a singularity. The mathematics tells us it's a point of infinite density, zero volume, a place where all the mass of the black hole is compressed into nothing at all, dimensionless and impossible. But here's the thing, when physicists talk about the singularity, they're also admitting something profound. Our theories break down there. General relativity, which describes gravity and space-time so beautifully everywhere else, gives us infinities at the singularity. And in physics, infinities are usually a sign that we're missing something, that our equations are pushing beyond their domain of validity. Quantum mechanics, which governs the very small, should matter at the singularity. But we don't yet have a complete theory that unifies quantum mechanics with general relativity. So the singularity remains a mystery, a question mark at the heart of every black hole. Maybe it's not really a point of infinite density. Maybe quantum effects smooth it out into something else, a tiny but finite region, or a connection to something we haven't imagined yet. The singularity is where the universe tells us, gently but firmly, you don't understand everything yet. There's more to learn. And somehow, I find that comforting. The idea that even our best theories have edges, places where the mystery begins again. Black holes aren't cosmic vacuum cleaners. They only pull in matter that comes very close to them. There's a common misconception about black holes, that they're ravenous monsters, sucking in everything around them like cosmic vacuum cleaners. Science fiction has certainly contributed to this image, showing black holes as whirlpools that devour entire star systems. But the reality is more nuanced and in a way more interesting. A black hole's gravity far away from it is no different from any other object's gravity of the same mass. If the sun magically became a black hole right now, don't worry, it can't. But imagine, Earth would continue orbiting exactly as it does today. We wouldn't be pulled in. We wouldn't spiral toward doom. We'd just orbit an invisible object instead of a bright star. Of course, we'd freeze in the darkness, but that's a different problem. Black holes only pull in matter that comes very, very close enough to cross the event horizon, or to be within the accretion disk. For everything else, they're just massive objects that curve space according to the normal rules. You could orbit a black hole safely, the way the moon orbits Earth, as long as you kept your distance. It's only when you get too close that the danger begins, that the gravity becomes inescapable. In a way, black holes are less like monsters and more like deep wells. Dangerous if you fall in, but perfectly safe if you walk carefully around the edge. The Schwarzschild radius determines how compressed an object must be to become a black hole. Every object has a Schwarzschild radius, a theoretical boundary. If you could compress that object down until it fit entirely within its Schwarzschild radius, it would become a black hole. For most objects, this radius is absurdly tiny compared to their actual size, which is why black holes are rare and require extreme conditions to form. Take Earth, for example. Our planet has a Schwarzschild radius of about 9 millimeters, roughly the size of a marble. If you could somehow compress all of Earth's mass into a sphere that small, it would become a black hole. Of course, no natural process could do this. The planet is held up by the electromagnetic forces between atoms, by the pressure of matter, by all the ordinary forces that keep things from collapsing. You'd need to override all of that to compress matter beyond anything possible in our everyday experience. The Sun's Schwarzschild radius is about 3 kilometers. Imagine crushing all that mass, 300,000 times Earth's mass, an enormous ball of fusion fire, down to a sphere smaller than a city. Again, it can't happen to the Sun naturally, but for much more massive stars, at the end of their lives, it can happen. When they run out of fuel, nothing holds them up anymore, and they collapse past their Schwarzschild radius in less than a second. It's a threshold, a line drawn in the mathematics of space-time. Cross it, and you've created something impossible to escape, a permanent dimple in the fabric of reality itself. Time slows down near a black hole due to gravitational time dilation, an effect predicted by Einstein's relativity. Time, we like to think, is constant. Seconds tick by at the same rate whether you're on a mountaintop or in a valley, whether you're moving or standing still. But Einstein showed us that time is more flexible than that, more strange. And nowhere is this strangeness more apparent than near a black hole. Gravitational time dilation means that time passes more slowly in stronger gravitational fields. The effect is tiny in everyday life, so small you'd never notice it, but physicists can measure it. Clocks at sea level run slightly slower than clocks on mountaintops, by billionths of a second. GPS satellites have to account for this, or they'd drift out of sync with clocks on Earth's surface. Near a black hole, though, time dilation becomes extreme. If you could hover just outside the event horizon, and it would take an enormous amount of energy to stay there, fighting against the gravity, time would pass incredibly slowly for you compared to someone far away. Minutes for you might be years, decades, even centuries for them. You'd be living in slow motion relative to the rest of the universe, though you wouldn't feel any different. Your heartbeat, your thoughts, the light falling around you, it would all seem normal to you. It's one of those things that sounds like science fiction, but is absolutely real. A consequence of how gravity curves not just space, but time itself. The universe, it turns out, has no universal clock. Time is local, personal, dependent on where you are and how fast you're moving. From the perspective of someone falling in, they'd cross the event horizon in finite time, noticing nothing particularly special at that exact moment. Here's one of the most counterintuitive things about black holes. What you see depends entirely on where you're watching from. Imagine you're watching a friend fall toward a black hole's event horizon. As they get closer, you'd see them slow down. The light from them would become redder and dimmer, stretched out by the extreme gravity. Eventually, they'd appear to freeze at the horizon, their image fading away, but never quite crossing. From your perspective, they'd be stuck there forever, painted on the edge of the black hole, asymptotically approaching but never reaching the point of no return. But from your friend's perspective, if they could somehow send you a message, which they can't because nothing escapes, the experience would be completely different. They'd fall through the event horizon in finite time. No freezing, no stopping. To them, the crossing might not even seem dramatic. For a large enough black hole, the tidal forces at the horizon are gentle. They might not feel anything unusual at that exact moment. They'd simply cross the boundary and keep falling inward. What's strange is that both perspectives are valid. There's no contradiction, exactly. Just two different ways of slicing up space-time, two different stories about the same event. Your friend crosses in finite proper time, time measured by their own clock. But in the time coordinate you use far away, they never quite cross. It's a bit like how two people can take different paths between 2 points and measure different distances. Except here, it's time that's different. The universe doesn't have one single story. It has as many stories as there are observers. Spaghettification is the real scientific term for what happens when tidal forces stretch objects falling into a black hole. Sometimes astronomers have a sense of humor about the horrors of the cosmos. Spaghettification is the actual technical term, used in papers, in textbooks, spoken at conferences with straight faces, for what happens when you fall into a black hole and the tidal forces stretch you into a long, thin strand. Here's why it happens. Gravity gets stronger the closer you are to a massive object. Normally, this difference is negligible. Your head and your feet feel roughly the same gravitational pull from Earth. But near a black hole, the difference becomes extreme. If you're falling feet first toward a stellar mass black hole, your feet feel much stronger gravity than your head. The difference is enough to pull you apart, stretching you vertically while compressing you horizontally. You'd become thinner and longer, stretched like taffy, like pasta, like a human noodle. It's not a pleasant image, admittedly, but there's something almost absurdly poetic about it, that the universe's most extreme gravitational fields would turn us into cosmic spaghetti. For smaller black holes, this would happen well before you reached the event horizon. You'd be torn apart by the tidal forces long before you crossed the point of no return. But here's the interesting part. For supermassive black holes, the ones millions or billions of times the sun's mass, you could cross the event horizon intact. The tidal forces at the horizon are gentler when the black hole is larger. You'd have a few moments, maybe longer, falling through that invisible boundary, still whole, still yourself, before the forces deeper inside eventually pulled you apart. It's a strange kind of mercy, if you can call it that. For supermassive black holes, you could cross the event horizon without being spaghettified immediately. Let's linger on this idea for a moment, because it's genuinely strange and worth contemplating. If you fell toward the supermassive black hole at the center of our galaxy, Sagittarius A, which we'll talk more about later, you could cross the event horizon and survive it. Not forever, of course, not for long, but for those first moments after crossing, you'd be okay. The tidal forces wouldn't tear you apart immediately. You'd fall through that invisible boundary, the point of no return, the edge beyond which the universe offers no path back, and you might not even notice. Around you, space would look strange. The universe outside would appear distorted, compressed into a bright ring of light. But you wouldn't feel a barrier, wouldn't hit a wall. You'd just keep falling. Eventually, as you fell deeper, the tidal forces would grow. The singularity at the center would loom closer in space-time, if not in any direction you could point to, and those forces would become unsurvivable. But for a little while, you'd have a window, a strange, doomed window, to experience what it's like inside a black hole. Of course, you could never tell anyone. No signal could escape to share what you saw. Your experience would be private, final, a story that ends without an audience. There's something both lonely and profound about that. The idea that some experiences, some journeys, have no witnesses but yourself. Black holes can spin, and this rotation drags the fabric of space-time around them like a whirlpool. Black holes don't have to be perfectly still. In fact, most probably aren't. They can spin, rotating around an axis just like planets or stars. And when they spin, something remarkable happens. They drag space-time itself along with them. This effect is called frame dragging, or sometimes the lens-thirring effect, after the physicists who first predicted it. Imagine space-time as a thick fluid, like honey or molasses. When the black hole spins, it's like a spoon stirring that fluid, creating a vortex, a whirlpool in the fabric of reality itself. Near a spinning black hole, space isn't just curved, it's moving. If you tried to stay still relative to the distant stars, you'd find yourself being pulled along in the direction of the black hole's spin. It's not that you're being pushed by anything physical. It's that the very definition of staying still has changed. Space itself is rotating and you're embedded in it. Far from the black hole, this effect is subtle, barely measurable. But close to the event horizon, it becomes dramatic. The faster the black hole spins, the more it drags space. With it, creating a region called the ergosphere, which sounds like something from science fiction, but is very real, where nothing can remain stationary. Even light gets dragged along. It's one of those ideas that makes you reconsider what you mean by empty space. It's not a static stage where events play out. It's dynamic, flexible, something that can bend and twist and flow. The universe is stranger than it seems. The ergosphere is a region outside a rotating black hole's event horizon, where nothing can remain stationary. The ergosphere deserves its own moment of attention because it represents something genuinely bizarre, a place where standing still becomes impossible, not because you lack the energy, but because the geometry of space-time forbids it. Imagine you're in a spacecraft near a rapidly spinning black hole, outside the event horizon, but inside the ergosphere. You fire your engines at full power, trying to hover in place relative to the distant stars. But you can't. Space itself is being dragged around the black hole so strongly that even at full throttle, even at speeds approaching light itself, you get pulled along in the direction of the spin. It's not that you're falling in. You're still outside the event horizon, still capable of escaping if you wanted to. But you can't stop rotating around the black hole. You're forced to move with the flow of space-time, like a leaf caught in a current. You can swim harder or softer, spiral outward or inward, but you can't stop the sideways motion. The ergosphere's outer boundary is called the static limit, the surface beyond which you can no longer remain static. Inside it, you must move. The very concept of rest ceases to exist. It's one of those things that sounds metaphorical, but is literally true. The universe has created a region where stillness is geometrically impossible. And yet, despite this forced motion, you could still escape. The ergosphere isn't a trap, just a place where the rules have changed. You'd have to move with the spin, but you could still work your way back out, back to calmer space-time, back to a place where holding still is once again possible. Some black holes spin at nearly 99% of the maximum possible rate, approaching the theoretical speed limit. Black holes have a maximum spin rate. Physicists call it the extremal limit, the point at which the black hole is spinning as fast as physics allows. At this maximum, the event horizon would be spinning at nearly the speed of light, and the black hole would be as flattened as possible, bulging at its equator. We've found black holes that appear to be spinning at, or very close to, this maximum rate. These are called near-extremal, or maximally rotating black holes, and they're fascinating objects. At such extreme spins, the ergosphere extends far out from the event horizon, and the frame-dragging effects are enormous. What's interesting is how they got spinning so fast. When a black hole forms from a collapsing star, it inherits some of the star's rotation, but to spin at near maximum rates, it probably needed to accrete matter in a very organized way, pulling in material from an accretion disk that's all rotating in the same direction, gradually spinning up the black hole like a figure skater pulling in their arms. There's something almost elegant about the idea of these cosmic spinners, rotating at the edge of what's possible. They're pushing against a fundamental limit, not because anything is stopping them physically, but because the mathematics of space-time sets a boundary. Spin faster than this, the equations seem to say, and you'd create a naked singularity, a singularity without an event horizon, which most physicists believe is impossible. The no-hair theorem states that black holes can be completely described by just three properties: mass, spin, and electric charge. This is one of my favorite names in all of physics, the no-hair theorem. It sounds whimsical, almost silly, but it describes something profound about the nature of black holes. The theorem says that a black hole can be completely described by only three numbers: its mass, how fast it's spinning, and its electric charge. That's it. Nothing else matters. It doesn't matter if the black hole formed from a star made of hydrogen or iron or exotic matter. It doesn't matter what shape the collapsing object was, whether it was smooth or lumpy, whether it had planets orbiting it or was alone in space. Once it becomes a black hole, all of those details are erased. This is what physicists mean when they say black holes have no hair. All the complex details, the hair, get smoothed away, leaving only those three fundamental properties. Two black holes with the same mass, spin, and charge are identical, indistinguishable, no matter how differently they formed. It's a kind of cosmic amnesia, a way the universe forgets information. And that forgetting is part of what makes black holes so puzzling, especially when you start thinking about quantum mechanics and information theory. How can all that information just disappear? Is it really gone, or is it stored somewhere we haven't figured out yet? The no-hair theorem is simple to state, but its implications ripple through theoretical physics, touching on some of the deepest questions we have about reality. Most black holes probably have negligible electric charge, despite the possibility of charged black holes existing. In principle, a black hole could have an electric charge. The mathematics allows for it. Schwarzschild solved the equations for non-spinning, uncharged black holes, but there are other solutions for charged ones, called Reissner-Nordström black holes, and even charged spinning ones, called Kerr-Newman black holes. But in practice, we don't expect to find many charged black holes out there in the universe. Here's why. Matter, on average, is electrically neutral. For every electron, there's roughly a proton. For every negative charge, a positive. So when a star collapses to form a black hole, the black hole inherits roughly neutral matter. Even if a black hole did start with some net charge, it wouldn't stay that way for long. A positively charged black hole would attract negatively charged particles from its surroundings, electrons, negative ions, and repel positive ones. This would quickly neutralize the charge. The same thing would happen in reverse for a negatively charged black hole. So while the mathematics of charged black holes is beautiful and worth studying, they're probably rare in nature, if they exist at all. Most black holes are likely described by just two of those three properties: mass and spin. The charge for most purposes is effectively zero. Still, it's worth knowing that the universe allows for them in principle. The equations don't forbid charged black holes, even if nature rarely makes them. It's a reminder that theoretical possibilities and common occurrences aren't always the same thing. Black holes emit no light themselves, but they can be the brightest objects in the universe due to their surrounding matter. Here's a beautiful irony. Black holes themselves are perfectly dark. They emit no light, no radiation that we can see, except for that faint Hawking radiation, which we'll get to much later. And yet, they can be responsible for some of the most brilliant light shows in the entire cosmos. When a black hole is actively feeding, pulling in gas and dust from its surroundings, that material doesn't fall straight in. It forms what's called an accretion disk, a swirling disk of matter spiraling inward. As the material orbits closer and closer, it moves faster and faster, and friction heats it up enormously. The inner parts of the accretion disk can reach temperatures of millions of degrees. At those temperatures, matter glows brilliantly, emitting light across the spectrum: visible light, ultraviolet, X-rays. The region immediately around a feeding black hole can be brighter than entire galaxies, outshining billions of stars. So while the black hole itself remains invisible, a perfect absorber of light, it's surrounded by this blazing halo of tortured matter. The darkness at the center creates the brilliance around the edges. There's something poetic about that the darkest objects in the universe also create some of the brightest light, that emptiness and radiance are intimately connected. When we see a black hole, what we're really seeing is its shadow, its absence, defined by the glow of everything falling toward it. The first black hole candidate, Cygnus X1, was discovered in 1964 through X-ray observations. For decades, black holes were purely theoretical, mathematical curiosities hidden in Einstein's equations, objects that could exist but which no one had ever found. And then, in 1964, astronomers detected something unusual, a powerful source of X-rays in the constellation Cygnus, the Swan. They called it Cygnus X1. The X-rays were coming from a region of space where there was a bright blue supergiant star, but the star itself wasn't producing the X-rays. Something else was there, something invisible, orbiting the star and pulling material away from it. As that stolen material spiraled inward toward the unseen object, it heated up and emitted those powerful X-rays. By studying the orbit of the visible star, astronomers could infer the mass of its invisible companion. And that mass was too large, much too large, to be a neutron star, which was the only other compact object they knew about. It had to be something else, something that matched the theoretical predictions for a black hole. Still, there was skepticism. For years, some astronomers weren't fully convinced. Stephen Hawking even made a bet with physicist Kip Thorne in 1974, Hawking betting against Cygnus X1 being a black hole, Thorne betting for it. Hawking later conceded the bet, acknowledging that the evidence had become overwhelming. Cygnus X1 was our first glimpse of something we'd predicted but never seen. A real black hole, out there in the cosmos, betraying its presence by what it did to everything around it. It was the beginning of a new era in astronomy, the moment when black holes stopped being purely theoretical and became observational reality. We detect black holes primarily through their effects on nearby matter and space-time, not by seeing them directly. Black holes are invisible by definition. They don't emit light, and light falling toward them never comes back out. So how do we find them? How do we study something we can't see? The answer is that we watch what they do to everything around them. We look for their influence, their gravitational fingerprints, the way they disturb the fabric of space-time and the matter embedded in it. Sometimes we detect them through X-ray emissions, like Cygnus X1, the superheated accretion disk glowing brightly as matter spirals inward. Sometimes we find them by watching stars orbit around invisible companions, calculating the mass needed to create those orbits, and finding it exceeds anything but a black hole. Sometimes we detect the gravitational waves they produce when they merge with other black holes, ripples in space-time itself that travel across the universe at the speed of light. And sometimes now we can even image their shadows, the dark silhouette they cast against the bright background of their accretion disks. It's a bit like studying the wind. You can't see the wind itself, but you can see leaves rustling, trees bending, dust swirling. From those effects, you can map the invisible currents moving through the air. Black holes are similar, invisible dancers whose presence we infer from how their partners move, from the distortions they create, from the energy they release. In a way, it makes them more mysterious, more compelling. They're objects we know primarily through absence and influence, through what they're not rather than what they are. Binary systems where a black hole orbits a visible star provide some of our best evidence for stellar mass black holes. Picture two dancers circling each other, locked in a gravitational embrace. One is visible, a normal star shining with its own light. The other is invisible, dark, present only in its influence on its partner's motion. These binary systems are some of our best laboratories for studying stellar mass black holes. When a black hole and a normal star orbit each other, we can watch the visible star's motion, how it wobbles, how fast it moves, the period of its orbit. From that motion, using the same laws of gravity that describe planets orbiting the sun, we can calculate the mass of the invisible companion. If that mass is too large to be a neutron star, roughly above 3 solar masses, though the exact limit is still debated, then it must be a black hole. There's nothing else it could be. No other kind of object can be that massive and that compact without collapsing into a black hole. Often, the black hole is pulling material away from its companion star, especially if the star has expanded into a red giant. A stream of gas flows from the visible star toward the black hole, forming an accretion disk that glows with X-rays. This makes the system easier to spot, like a cosmic beacon marking the presence of something dark. Dozens of these systems have been found in our galaxy alone. Each one tells a story of stellar evolution, of one star dying and collapsing while its companion lives on, of strange partnerships between light and darkness, visibility and absence. In 2019, the Event Horizon Telescope captured the first direct image of a black hole's shadow. April 10th, 2019. That was the day humanity saw a black hole for the first time. Not inferred from X-rays or gravitational waves, not calculated from orbital mechanics, but actually imaged. A photograph of sorts, of the shadow cast by a black hole against the glow of its accretion disk. The black hole was at the center of a galaxy called Messier 87, about 55 million light-years away. It's a supermassive black hole, 6.5 billion times the mass of our Sun, and there it was on our screens, a bright ring of light surrounding a dark circle, exactly as Einstein's equations predicted, exactly as physicists had simulated. The image looked almost surreal in its clarity, in how well it matched theory. The dark center was the black hole's shadow, not the event horizon itself, which is much smaller, but the region around it from which light cannot escape or reach us. The bright ring was the photon sphere, light from the accretion disk that's been bent around the black hole by its extreme gravity. What struck me, seeing that image, was how it made something abstract suddenly concrete. For decades, black holes were equations, models, artists' conceptions. And suddenly there was this photograph, proof that the mathematics we'd trusted, the theory we'd developed, actually described something real. The universe confirmed what our minds had imagined. It was a triumph of human ingenuity, of collaboration, of our ability to see things we have no right to see given how small we are, how brief our lives, how vast the cosmos. And yet we managed it. The M87 black hole image required synchronizing 8 radio telescopes across the planet, creating an Earth-sized virtual telescope. To capture that image of the M87 black hole, astronomers had to do something extraordinary. They had to turn the entire Earth into a telescope. No single telescope could do it alone. The black hole, despite being enormous, is so far away that it appears tiny in the sky, about the same angular size as an orange on the moon as seen from Earth. To image something that small requires incredible resolution, which in turn requires a telescope with an enormous effective diameter. So they synchronized 8 radio telescopes scattered across the planet, in Hawaii, Arizona, Mexico, Chile, Spain, and Antarctica. Each telescope collected radio waves from the black hole simultaneously, recording not just the waves themselves, but their exact timing. Later, powerful computers combined all that data using a technique called very long baseline interferometry to create a single image as if from a telescope the size of Earth itself. The amount of data was staggering, about 5 petabytes, roughly equivalent to the entire lifetime of selfies from 40,000 people. It was too much to transmit over the internet, so they physically shipped hard drives to processing centers. The data from the Antarctic telescope couldn't be retrieved until the Antarctic winter ended months later. What emerged from all that data, all that coordination, all that patient analysis, was that single image, a ring of light around darkness, an Earth-sized eye, open for just a moment, glimpsing the shadow of a black hole 55 million light-years away. It's humbling and inspiring at the same time, what we can achieve when we work together, when we turn our attention toward understanding rather than conquest. In 2022, astronomers revealed the first image of Sagittarius A, the supermassive black hole at our galaxy's center. 3 years after imaging the M87 black hole, astronomers achieved something even more challenging. They imaged Sagittarius A, the black hole at the heart of our own Milky Way galaxy. You might think this would be easier. After all, Sagittarius A is much closer, only about 26,000 light-years away compared to M87's 55 million. But proximity brought its own challenges. Sagittarius A is much smaller, about 4 million solar masses compared to M87's 6.5 billion, and its accretion disk changes on timescales of minutes rather than weeks. Trying to image it was like photographing a toddler who won't sit still compared to the relatively patient adult that M87 represented. The team had to develop new analysis techniques, finding patterns in data that was constantly shifting and changing. They essentially created thousands of possible images and looked for common features, for the underlying structure that persisted despite the chaos. And once again, the result matched theory beautifully. A ring of light around a dark center, our galaxy's beating heart made visible for the first time. This black hole has been at the center of our galaxy for billions of years, holding everything together through its gravity, and we've only just now managed to actually see its shadow. There's something poignant about that we've lived our entire existence in a galaxy with a supermassive black hole at its center, orbiting around it without knowing. And only now, only recently, have we developed the tools to glimpse what we've been orbiting all along. Gravitational waves from merging black holes were first detected in 2015, confirming a century-old prediction by Einstein. September 14th, 2015. 2 black holes, each several dozen times the mass of our sun, completed a dance that had lasted millions of years. They spiraled together, closer and closer, until in a fraction of a second they merged, releasing more energy than all the stars in the observable universe combined. That energy didn't come out as light or heat. It came out as gravitational waves, ripples in the fabric of space-time itself, spreading outward at the speed of light, and 1.3 billion years later, those ripples reached Earth. The LIGO detectors in Louisiana and Washington, enormous L-shaped instruments designed to measure distances with impossible precision, felt space-time itself flex and stretch as the wave passed through. The distortion was tiny, far smaller than the width of a proton, but it was measurable, and it matched, precisely, the predictions for what gravitational waves from merging black holes should look like. Einstein had predicted gravitational waves a century earlier, as a consequence of general relativity. He thought they'd be too weak to ever detect, but we built instruments sensitive enough, waited patiently enough, and the universe rewarded us with this signal. A chirp, they called it, because of the rising pitch as the black holes spiraled faster and faster before merging. It was the first time we'd heard the universe rather than seen it. A new sense, a new way of observing, opening up a universe that had been silent to us before. When black holes merge, they ring like bells, producing gravitational waves with characteristic frequencies. After 2 black holes merge, something beautiful happens. The newly formed black hole isn't perfectly smooth, not immediately. The violence of the merger leaves it distorted, oscillating like a bell that's just been struck. These oscillations are called quasi-normal modes, and they produce gravitational waves at specific frequencies, determined by the black hole's mass and spin. The black hole is literally ringing, vibrating in space-time, and those vibrations ripple outward as waves we can detect. The ring-down, as it's called, lasts only a fraction of a second. The black hole quickly settles into its final, smooth shape, as described by that no-hair theorem we talked about earlier. But during that brief moment, it's telling us about itself, its mass, its spin, even testing whether general relativity's predictions are correct. Different oscillation modes produce different frequencies, like how a bell produces not just one note, but a whole spectrum of harmonics. By analyzing these frequencies, astronomers can essentially perform spectroscopy on space-time itself, learning about the properties of the final black hole from the sound it makes as it settles. There's something almost musical about it. The idea that massive cosmic events produce literal tones, that black holes sing their properties into the universe in the moments after they form. We can't hear it with our ears, of course. The frequencies are far too low, and they're vibrations in space-time rather than air. But our instruments can hear them, and they're teaching us to listen to the universe in a new way. Some black hole mergers release more energy in a fraction of a second than all the stars in the observable universe combined. Let's pause for a moment on that fact, because it's genuinely hard to comprehend. All the stars in the observable universe, hundreds of billions of galaxies, each containing hundreds of billions of stars. Every photon they emit, every bit of light shining into the darkness, add it all up, every star burning, every fusion reaction, every ounce of radiation being released into space across the entire visible cosmos. When two massive black holes merge, they can release more energy than all of that, but compressed into a fraction of a second. Most of that energy comes out as gravitational waves, waves in space-time itself, rather than light, which is why we don't see these events optically. But the amount of power involved is almost unimaginable. To be clear, it's not that they're creating energy from nothing. What's happening is that some of the mass of the black holes, the mass energy locked up in their gravitational fields, is being converted into gravitational waves, following Einstein's famous EAOMC2. Even a small fraction of the mass of a black hole represents an enormous amount of energy. But still, the sheer power of these events is staggering. For that brief moment, that cosmic instant, nothing else in the universe is releasing energy as quickly. It's a reminder of the scales involved, of how much energy is bound up in gravity, in the curvature of space-time, in the deep structure of reality itself. And all of it happens in darkness, visible only to our most sensitive instruments, felt only as the gentlest trembling in the fabric of space. Astronomers have detected gravitational waves from dozens of black hole mergers, each revealing cosmic collisions from the distant past. Since that first detection in 2015, the floodgates have opened. We've now detected gravitational waves from dozens of black hole mergers, each one a message from the deep past, from events that happened millions or even billions of years ago. Every detection tells a story. Two black holes, formed from massive stars that exploded as supernovae, somehow found each other across the vastness of space. Maybe they formed together in a binary system, orbiting each other from birth. Maybe they met in the crowded center of a dense star cluster, where chance encounters can lead to gravitational captures. Over millions of years, they spiraled closer, their orbits decaying as they radiated gravitational waves. Too weak to detect then, at that early stage. But as they drew nearer, the waves grew stronger, the spiral faster. In the final minutes, hours at most, the waves became powerful enough to reach across the cosmos. And in the final second, they merged, ringing that space-time bell, sending out their final announcement to the universe. Each merger is unique. Different masses, different spins, different distances from us. Some involve black holes that are surprisingly massive, challenging our theories of how such objects could form. Some show signs of precession, wobbling as they orbit like spinning tops. Each one refines our understanding, adds another data point, helps us map the population of black holes throughout the universe. We're building a census of the invisible, learning about objects we can never see directly, listening to the universe's deepest bass notes, and slowly, patiently, learning to read the stories they tell. Nearly every large galaxy has a supermassive black hole at its center, including our own Milky Way. There's something profound about this discovery, that galaxies and supermassive black holes seem to go together, like they're two parts of a single system rather than separate objects. We've surveyed hundreds of large galaxies, looking at their centers, studying the motion of stars and gas near the core. And almost always, we find the same thing: a supermassive black hole, millions or billions of times the mass of our sun, sitting at the very heart of the galaxy. Our own Milky Way is no exception. At its center, about 26,000 light-years away from us, sits Sagittarius A, that 4 million solar mass black hole we imaged in 2022. We've been orbiting around it our entire existence, our solar system, making a slow circle that takes about 225 million years to complete. Dinosaurs walked the Earth the last time we were in this part of our orbit. What's fascinating is that the mass of a galaxy's central black hole seems to correlate with properties of the galaxy itself, specifically with the velocity dispersion of stars in the galaxy's bulge. Somehow, processes happening at the scale of the black hole, just a few light hours across, are connected to processes happening across the entire galaxy, thousands of light years in size. This suggests they grew together, influenced each other, co-evolved over billions of years. The black hole shapes the galaxy through its energy output and gravitational influence. The galaxy feeds the black hole, funneling matter toward the center. They're partners in a cosmic dance, each affecting the other in ways we're still working to fully understand. Sagittarius A, our galaxy's central black hole, has a mass of about 4 million suns, but is relatively quiet right now. Sagittarius A is, in cosmic terms, a bit of an underachiever at the moment. It's there, massive and undeniable, but it's not doing much. It's on a diet, you might say, consuming very little material, producing relatively little radiation. We can track individual stars orbiting close to it, some completing their orbits in just a few years. One star, called S2, orbits so close that it reaches speeds of about 3% the speed of light at its closest approach. By watching these stellar orbits, we can map the black hole's gravitational influence with remarkable precision, even though we can't see the black hole itself, or couldn't, until that 2022 image. But despite its mass, Sagittarius A is remarkably dim. It's not surrounded by a bright, massive accretion disk like some galactic centers. It flickers occasionally, flares up for brief moments, when some unfortunate cloud of gas wanders too close, but mostly it's quiet, starved, waiting. This wasn't always the case. There's evidence that in the past, maybe just a few hundred years ago, Sagittarius A was more active, bright enough to illuminate vast clouds of gas thousands of light years away, clouds that still glow faintly with the echo of that ancient light. We're seeing the aftermath, the fading memory of a time when our galaxy's heart burned brighter. Someday it might feed again, if another gas cloud drifts too close, or if a star wanders into its gravitational grasp. Sagittarius A will wake up, brightening dramatically. But for now it's dormant, a sleeping giant at the center of our cosmic home. The largest known black holes have masses exceeding 60 billion times that of our Sun. 4 million solar masses sounds enormous, and it is, by any normal standard. But in the hierarchy of supermassive black holes, Sagittarius A is actually rather modest. Some black holes dwarf it, reaching masses that seem almost absurd in their magnitude. The largest confirmed black holes have masses exceeding 60 billion times that of our Sun. To put that in perspective, if you replaced our Sun with one of these ultramassive black holes, its event horizon would extend well past the orbit of Neptune. The entire inner solar system, all the rocky planets, the asteroid belt, even Jupiter and Saturn, would fit comfortably inside. These monsters typically reside at the centers of the most massive elliptical galaxies, ancient systems that have grown through countless mergers and acquisitions. Each time two galaxies merge, their central black holes eventually find each other and merge as well, building up mass over billions of years. But there's a puzzle here. We don't fully understand how black holes can grow this large, even if they've been feeding continuously since the early universe. Even if they've merged with many other black holes, the growth rate needed to reach these masses is faster than our models easily allow. There's a limit to how quickly a black hole can accrete matter, feed too fast, and the radiation pressure from all that infalling material pushes new material away, choking off the supply. So either these ultramassive black holes found ways to feed very efficiently, or they started with much larger seeds than we thought, or something about our models is incomplete. It's one of those humbling reminders that even when we understand the basic physics, the universe can still surprise us with its extremes. We don't fully understand how supermassive black holes formed so early in the universe's history. Here's one of the deepest mysteries in modern astronomy. We've found supermassive black holes with masses of hundreds of millions or even billions of solar masses, existing less than 1 billion years after the Big Bang. That shouldn't be possible, or at least it shouldn't be easy. Black holes grow by accreting matter and by merging with other black holes. But there are limits to both processes. Accretion has that maximum rate we just mentioned, the Eddington limit, beyond which radiation pressure prevents further feeding. And mergers take time for black holes to find each other, time for their orbits to decay through gravitational wave radiation. If you start with stellar mass black holes, the kind formed from individual stars, and try to grow them to supermassive scales in less than 1 billion years, the math gets difficult. You need to feed them at or near the maximum rate constantly, with no breaks, and even then you might not make it to the masses we observe. So how did they get so big so fast? Maybe they formed differently, not from individual stars, but from the direct collapse of massive primordial gas clouds in the early universe, creating seeds that were already thousands or even hundreds of thousands of solar masses. Or maybe they grew through super Eddington accretion somehow, feeding faster than we think should be possible. Or maybe there's something about the early universe, its higher densities, different conditions, that we're not accounting for properly. It's an active area of research, and the answer might reshape our understanding of the early universe, of how structures formed, of how matter and energy behaved in that distant cosmic dawn. Supermassive black holes may have formed from the direct collapse of massive gas clouds in the early universe. One of the leading ideas for solving that early supermassive black hole puzzle is called direct collapse. Instead of forming from stars, maybe some black holes form directly from huge clouds of primordial gas. In the early universe, conditions were different. Gas clouds could be more massive, and in certain special environments, particularly in regions where normal star formation was suppressed, these clouds could collapse directly into black holes without ever forming stars first. Imagine a cloud of hydrogen and helium, hundreds of thousands of times the sun's mass, collapsing under its own gravity. Normally, as such a cloud collapses, it would fragment into smaller pieces, each forming a star. But if the conditions are just right, if there's enough radiation from nearby sources to keep the gas hot and prevent fragmentation, if there's no molecular hydrogen to cool the gas efficiently, the cloud might collapse as a single object. When it reaches sufficient density, instead of igniting fusion and becoming a star, it just keeps collapsing, past all the usual stopping points until it forms a black hole. Not a stellar mass black hole, but one that already has thousands or hundreds of thousands of solar masses. A head start on the path to becoming supermassive. These direct collapse black holes, if they exist, would solve part of the puzzle. Start with a bigger seed, and you have an easier time growing to supermassive scales in the time available. But proving they actually formed this way is challenging. We need to find their signatures in the early universe, distinguish them from black holes that grew through other means, detective work at cosmic scales, looking for clues in light that's been traveling for most of the universe's history. The relationship between a galaxy's mass and its central black hole's mass suggests they co-evolve. Here's something that surprised astronomers when they first discovered it. The mass of a galaxy's central black hole is tightly correlated with the velocity dispersion of stars in the galaxy's bulge. That's a technical way of saying that the black hole's mass is related to how fast stars are moving in the inner part of the galaxy. Why should this be? The black hole is tiny compared to the galaxy. Sagittarius A's event horizon is smaller than Mercury's orbit, while the Milky Way stretches 100,000 light years across. The scales are so different that you might think they'd be unrelated. And yet somehow they know about each other. Somehow they grow in proportion. This suggests a feedback relationship, a dialogue between the black hole and its host galaxy. When the black hole feeds actively, it releases enormous amounts of energy, radiation, winds, jets. That energy can heat gas throughout the galaxy, preventing it from cooling and forming stars. It can even drive gas out of the galaxy entirely, shutting down star formation. At the same time, the galaxy provides food for the black hole. gas clouds that drift inward, material from mergers with other galaxies. When the galaxy grows through mergers, its black hole grows too, both through accretion and through merging with the other galaxy's black hole. They regulate each other, in a sense. The black hole keeps the galaxy from growing too quickly by suppressing star formation. The galaxy's mass determines how much material is available to feed the black hole. It's a kind of cosmic symbiosis, a partnership that shapes both objects over billions of years. Understanding this relationship is key to understanding how galaxies evolve, how they form their structures, why they look the way they do. The black hole, despite being such a tiny fraction of the galaxy's total mass, plays an outsized role in the galaxy's life story. Active galactic nuclei powered by supermassive black holes can be bright enough to outshine their entire host galaxy. When a supermassive black hole is actively feeding, when it has a steady supply of gas and dust falling into it, it doesn't stay quiet. It becomes an active galactic nucleus, or AGN, one of the most luminous objects in the universe. The accretion disk around an actively feeding supermassive black hole can be astonishingly bright, emitting more light than all the galaxy's stars combined. We're talking about an object smaller than our solar system, outshining 100 billion stars. The radiation spans the spectrum: radio waves, visible light, X-rays, gamma rays, a cosmic beacon visible across billions of light years. From a distance, the galaxy might appear to have a brilliant point of light at its center, so bright that it drowns out the diffuse glow of the surrounding stars. Early astronomers, before they understood what they were seeing, cataloged these objects as unusual stars. They called them quasi-stellar objects, or quasars for short, because they looked like stars, but their spectra were bizarre, showing properties that no star could produce. Later we realized these aren't stars at all. They're the brilliant hearts of distant galaxies, supermassive black holes in their feeding phase, releasing energy at rates that challenge imagination. The material spiraling into the black hole is heated to millions of degrees, glowing with a ferocity that nothing else in nature can match. And yet, despite all this light, the black hole itself remains dark, hidden behind the brilliance of its accretion disk. We see the effects, the transformation of gravitational potential energy into radiation, but the black hole itself stays invisible, a dark conductor orchestrating a luminous symphony. Quasars are extremely distant and luminous active galactic nuclei, visible from billions of light years away. Quasars are time machines, in a sense. When we observe them, we're seeing the universe as it was billions of years ago, when the cosmos was younger, denser, more turbulent. Most quasars we observe are at enormous distances. Their light has been traveling for most of the age of the universe to reach us. This means we're seeing them as they were in the past, in the early universe when conditions were very different. Back then, galaxies were merging more frequently, gas was more abundant, and supermassive black holes had more fuel available. The quasar era, the time when quasars were most common, peaked about 10 billion years ago, when the universe was only about a quarter of its current age. That's when black holes were feeding most voraciously, when the universe was lit up by these brilliant beacons scattered throughout space. Today, quasars are much rarer. Most supermassive black holes, including our own Sagittarius A, are relatively quiet, having exhausted the easily accessible fuel in their surroundings. The universe has aged into a more settled state, where violent feeding events are less common. But looking at distant quasars allows us to study that earlier, more active era. We can learn about black hole growth, about galaxy formation, about the conditions in the early universe. Each quasar is a snapshot from a particular time and place, a fossil record written in light, preserved by the vast distances involved, and only now reaching our telescopes. It's humbling to think that the light we're collecting from some quasars began its journey before Earth existed, before the sun formed, traveling through expanding space for billions of years until it happened to fall into our instruments, carrying news of events from an ancient cosmos. Some supermassive black holes launch jets of particles at nearly the speed of light, extending for millions of light years. Not all of the material falling toward an active supermassive black hole actually makes it in. Some of it, a surprisingly large amount, gets redirected, launched outward in narrow jets perpendicular to the accretion disk. These jets are among the most energetic phenomena in the universe. They shoot out at speeds approaching the speed of light, carrying matter, energy, and magnetic fields. They can extend for millions of light years, far larger than the galaxy itself, creating enormous structures that glow in radio waves. We're still working out the exact mechanism that produces these jets, but it seems to involve the interaction between the black hole's spin, the accretion disk's magnetic fields, and the ergosphere we talked about earlier. The rotating black hole somehow acts like a cosmic engine, tapping into its rotational energy and the gravitational potential energy of the infalling matter to power these relativistic outflows. The jets can have profound effects on the surrounding space. They plow through the intergalactic medium, creating bubbles and cavities in the hot gas between galaxies. They can trigger or suppress star formation in their host galaxies. They can even affect the evolution of galaxy clusters, redistributing energy over enormous volumes of space. When I think about these jets, streams of matter moving at near light speed, extending for distances that dwarf galaxies, powered by black holes that are themselves smaller than our solar system, I'm struck by the range of scales involved. From the event horizon, measured in light hours, to jets spanning millions of light years. The radiation and winds from active, supermassive black holes can actually suppress star formation in their galaxies. Here's a strange kind of irony: the black hole at a galaxy's center, despite being a tiny fraction of the galaxy's total mass, can control whether new stars form throughout the entire galaxy. When a supermassive black hole is actively feeding, it releases enormous amounts of energy. Some of this energy heats the gas in and around the galaxy to such high temperatures that it can't collapse to form stars. Gas needs to be cool and dense to form stars. Once it's too hot, it simply can't condense under gravity. Additionally, powerful winds and jets from the black hole can physically push gas out of the galaxy entirely, removing the raw material needed for star formation. This is called AGN feedback, the black hole feeding back energy into its environment, regulating its own food supply in a way. This feedback helps explain why the most massive galaxies have stopped forming stars. They're filled with old, red stars and show little sign of new star formation, despite having plenty of gas available. That gas is being kept hot by their central black holes, prevented from cooling and collapsing. It's a kind of cosmic thermostat. The black hole grows by accreting gas, but as it grows and becomes more active, it heats the surrounding gas, reducing the accretion rate. The system reaches a balance, a steady state where the black hole regulates its own feeding. Without this feedback, galaxies would look very different. They'd probably be more massive, filled with more stars. Their structures would be different. The black hole, for all its darkness, for all that it consumes and never returns, plays a crucial role in shaping the visible universe, in determining what becomes stars and what remains as diffuse gas, never to shine. When a massive star exhausts its nuclear fuel, its core collapses in less than a second. For millions of years, a massive star lives in balance. At its core, nuclear fusion converts hydrogen to helium, helium to carbon, carbon to heavier elements, each stage burning hotter and faster than the last. The outward pressure from this fusion holds the star up against gravity's inward pull. It's a standoff, an equilibrium, gravity and fusion pressure locked in a struggle that defines the star's life. But fusion can only go so far. Eventually, the core fills with iron, and iron won't fuse, not in a way that releases energy. Fusing iron actually consumes energy rather than producing it. So when a massive star's core becomes iron, the game is over. There's no more fuel, no more pressure to hold things up. What happens next is almost incomprehensibly fast. The core, no longer supported, collapses. In less than a second, maybe a quarter of a second, maybe even less, the core shrinks from something the size of Earth to something just a few dozen kilometers across. Electrons are crushed into protons, forming neutrons. Matter reaches densities that exist nowhere else in the universe except in the collapsed cores themselves. The outer layers, suddenly finding nothing beneath them, fall inward. When they hit the rigid core, they bounce, creating a shock wave that rips back outward through the star. The star explodes, a supernova, briefly outshining its entire galaxy. But at the center, hidden in the violence, something new has been born. If the core is massive enough, if it's beyond that threshold of about 3 solar masses, even neutron pressure can't stop the collapse. It becomes a black hole. All of this, the collapse, the explosion, the birth of the black hole, in less time than it takes to blink. The supernova explosion that accompanies stellar core collapse may leave behind a black hole instead of a neutron star. There's a threshold somewhere in the cosmos, a line drawn by the laws of physics. On one side, collapsing stellar cores become neutron stars, strange, dense objects held up by neutron degeneracy pressure, lighthouses in the darkness if they happen to be pulsars. On the other side, they become black holes, crossing that point of no return, collapsing past all barriers. We're still working out exactly where that line is. It depends on the mass of the core after the supernova explosion has ejected the outer layers. Somewhere around 2 to 3 solar masses seems to be the boundary, though the exact value depends on the equation of state of nuclear matter, something we can't yet measure directly. Some supernovae leave behind neutron stars. We've found many of them, pulsing rhythmically as they spin, sending beams of radiation sweeping through space like cosmic lighthouses. Other supernovae leave behind black holes, though these are harder to confirm since black holes don't announce themselves as obviously. And here's something poignant. When a neutron star forms, we can potentially study it for billions of years afterward, learning about its structure, its magnetic field, its gradual spin down. But when a black hole forms, almost all information about the original star is lost immediately. The no-hair theorem erases the details, leaves only mass, spin, and charge. It's as if the universe has two ways of preserving the memory of massive stars. Neutron stars that remain complex and studyable, or black holes that abstract everything away, reducing a star's entire history to just a few numbers. One path leads to continued complexity. The other leads to profound simplicity. Some stars may collapse directly into black holes without producing a visible supernova at all. Sometimes, not even a supernova marks the end. Some massive stars simply disappear, collapsing directly into black holes without the dramatic explosion we usually associate with stellar death. These are called failed supernovae, and they're both eerie and fascinating. Imagine a massive star, bright, visible, tracked by astronomers, and then over the course of months or years, it just fades away. No explosion, no light show, no nebula expanding into space. It just winks out, leaving behind nothing visible, or rather, leaving behind a black hole, but one that forms so quietly we barely notice. This happens when the collapsing core is so massive that the shock wave, the one that usually blows the outer layers away, stalls. Instead of bouncing back out, it loses energy, fails to propagate. The outer layers, instead of being ejected, just fall onto the growing black hole. The whole star collapses inward, and from the outside, we just see it dim and vanish. We think we've observed a few cases of this, stars that were there and then weren't, without any supernova detection. But they're hard to confirm because, well, the absence of something is harder to study than its presence. Did the star truly collapse, or did it just dim for other reasons? Did a black hole form, or something else? It's a quiet way to die for something so massive. No fanfare, no cosmic announcement, just a gradual fade from existence into invisibility. Sometimes the universe's most violent events happen almost in silence, marked only by what's no longer there. Intermediate mass black holes between stellar and supermassive have been difficult to find and confirm. There's a gap in our census of black holes, a missing population that should exist but which we've struggled to find. Between the stellar mass black holes formed from individual stars and the supermassive black holes at galactic centers, there should be intermediate mass black holes, objects ranging from hundreds to hundreds of thousands of solar masses. We have theoretical reasons to expect them. They could form from the collapse of very massive stars in the early universe, stars much larger than anything that exists today. Or they could form in dense star clusters, where black holes might merge repeatedly, building up mass over time. They might even be the seeds that grew into supermassive black holes. But finding them has proven challenging. They're not surrounded by large accretion disks like their supermassive cousins, so they don't produce the bright signatures of active galactic nuclei. And they're too massive to reveal themselves through the techniques we use to find stellar mass black holes in binary systems. There have been some promising candidates, some globular clusters, ancient dense collections of stars, show signs of having massive objects at their centers. Some gravitational wave detections have suggested black holes in the intermediate mass range, but confirmation is difficult, and the population remains largely mysterious. It's a reminder that for all we've learned, there are still basic questions about the black hole population that we can't fully answer. We can describe the physics of black holes beautifully, but knowing which ones actually exist, where they are, how many there are, that's observational work, and it's ongoing, patient, sometimes frustrating in its difficulty. Black holes grow by accreting matter from their surroundings and by merging with other black holes. A black hole, once formed, doesn't have to stay the same size. It can grow, adding to its mass through two main pathways, each one a story of cosmic accumulation. The first pathway is accretion, simply pulling in matter from the surroundings. Any gas, dust, or even unfortunate stars that wander too close can be captured, spiraling inward and eventually crossing the event horizon. Each bit of matter that falls in adds to the black hole's mass, making it slightly larger, slightly more massive, slightly harder to escape. The second pathway is merger. When two black holes spiral together and collide, they form a single larger black hole. The mass of the final black hole is slightly less than the sum of the two original masses. Some of the mass energy is radiated away as gravitational waves in that violent final moment. But most of it remains, combined into one object. Over cosmic time, through countless small accretion events and occasional dramatic mergers, black holes can grow substantially. A stellar mass black hole might accrete enough material over billions of years to double or triple its mass. Mergers in dense star clusters can build up intermediate mass black holes, and supermassive black holes at galactic centers grow through both pathways, feeding on gas clouds and stars, merging with other supermassive black holes when galaxies collide. It's patient growth, mostly. Not dramatic or fast, but steady, accumulating mass meal by meal, merger by merger, until small black holes become large ones, and large ones become supermassive. The universe has time for this gradual process, billions of years for black holes, to slowly increase their gravitational reach. The accretion disk around a feeding black hole can reach temperatures of millions of degrees. When matter falls toward a black hole, it doesn't usually plunge straight in. Instead, it forms a disk, a swirling, flattened structure of gas and dust spiraling gradually inward. And in that disk, something remarkable happens. Friction converts gravitational potential energy into heat, enormous amounts of heat. As material orbits closer to the black hole, it moves faster, following Kepler's laws. Different parts of the disk orbit at different speeds, and this creates friction, faster-moving inner material rubbing against slower-moving outer material. That friction generates heat, and the closer you get to the black hole, the more extreme the heating becomes. In the innermost regions of the accretion disk, temperatures can reach millions of degrees Kelvin. At those temperatures, atoms are fully ionized, electrons stripped away, leaving bare nuclei. The material glows brilliantly, emitting not just visible light, but ultraviolet radiation and X-rays. This is why we can detect black holes through X-ray observations. The superheated accretion disk is screaming its presence across the spectrum. It's one of nature's great ironies. The black hole itself is perfectly dark, but its appetite creates some of the brightest objects in the universe. The disk is incandescent with the energy of material on its final journey, like a funeral pyre announcing what's about to be lost forever. And all this heat, all this light, comes not from fusion or chemistry, but simply from matter falling, converting gravitational potential energy into radiation through the medium of friction. Gravity itself is lighting up the cosmos, inadvertently illuminating the very objects it's feeding. Not all matter in an accretion disk falls into the black hole. Some is ejected in powerful winds and jets. You might think that once matter enters the accretion disk, its fate is sealed. It will spiral inward until it crosses the event horizon. But the reality is more complex, more violent, and in some ways more interesting. A significant fraction of the material in an accretion disk never makes it to the black hole. Instead, it's expelled, blown away by radiation pressure, channeled into jets by magnetic fields, heated so much that it escapes the black hole's gravity entirely. The radiation from the inner disk is so intense that it can push on material further out, driving powerful winds that carry matter away from the black hole at speeds of thousands of kilometers per second. These winds can affect the surrounding galaxy, heating gas and potentially suppressing star formation. And then there are the jets we mentioned earlier. Narrow beams of material and energy shot out perpendicular to the disk at nearly the speed of light. The exact mechanism is still debated, but it involves the black hole's spin and strong magnetic fields threading through the disk. Somehow, this combination creates a cosmic accelerator, flinging material outward with tremendous energy. So the accretion disk is not just feeding the black hole, it's also a source of feedback, returning energy and matter to the environment. It's a leaky process, inefficient in a way, but that inefficiency is part of what makes black holes so influential. If all the matter fell straight in, black holes would be much quieter, less luminous, less important to their surroundings. Instead, they're messy eaters, and that messiness shapes galaxies, influences star formation, creates some of the most spectacular phenomena we observe. The black hole takes some and returns some, and both sides of that equation matter. Black holes in binary systems can strip material from their companion stars in a process called Roche-Lobe overflow. Imagine two dancers, close enough that their gravitational influences overlap, creating a complex choreography of forces and flows. In a binary system where one member is a black hole, something beautiful and strange can happen. The black hole can steal matter directly from its companion star. This happens through a process called Roche-Lobe overflow. Each object in a binary system has a gravitational domain, a region where its gravity dominates. These domains are called Roche lobes, and they touch at a point between the two objects. If a star expands, perhaps swelling into a red giant as it ages, it can fill its Roche lobe. Matter at the overflow point finds itself pulled equally by both objects, and from there, it's just a small step for it to spill over toward the black hole. What forms is a stream of gas flowing from the star to the black hole, like a bridge of matter connecting the two. The gas doesn't fall straight in. It has angular momentum, so it forms an accretion disk around the black hole, spiraling inward and heating up as it does. From the star's perspective, it's slowly being drained, losing mass to its invisible companion. Over millions of years, it might lose a significant fraction of its mass this way, becoming smaller, denser, while the black hole grows correspondingly larger. These systems can be luminous X-ray sources, the accretion disk glowing brilliantly as it converts the star's mass into radiation. They're some of our best laboratories for studying black hole accretion. for watching in real time as matter makes that final journey from star to black hole, visible and bright right up until the moment it crosses the event horizon and disappears from view. When two galaxies merge, their central supermassive black holes eventually sink toward the center and orbit each other. Galaxy mergers are slow-motion collisions, taking hundreds of millions of years to complete. When two galaxies begin to merge, their stars passing through each other, their gas clouds colliding and igniting new star formation, their central black holes begin a long journey toward each other. At first, they're far apart, each still near the center of its original galaxy. But as the galaxy's gravitational fields mix and settle, a process called dynamical friction causes the black holes to sink toward the center of the merged system. They're massive objects moving through a sea of stars and gas, and their gravity creates a wake, a drag that gradually slows them and pulls them inward. Eventually, after tens or hundreds of millions of years, the black holes get close enough to gravitationally bind to each other. They become a binary system, two supermassive black holes orbiting their common center of mass, perhaps separated by just a few light years, or even less. From there, the orbit continues to shrink. Interactions with nearby stars can carry away orbital energy, tightening the binary. Gaseous interactions can help too, but these mechanisms become less efficient as the black holes get closer, leading to something called the final parsec problem, a theoretical difficulty in getting the black holes from a separation of about a parsec down to the milliparsec scales, where gravitational wave emission becomes efficient. We think they do eventually merge. We've detected gravitational waves from supermassive black hole-sized systems. After all, though those detections are indirect, inferred from pulsar timing. But the exact pathway, the mechanisms that bridge that final gap, are still being worked out. The universe accomplishes it somehow, bringing these giants together despite the challenges. Before merging, binary black holes emit gravitational waves that carry away energy, causing the orbit to shrink. In the final stages, when two black holes are orbiting close together, gravitational waves take over the story. These ripples in space-time carry energy away from the system, and as they do, the orbit slowly shrinks. The black holes spiral closer and closer together, moving faster and faster as they approach. At first, when they're far apart, the gravitational wave emission is weak. The orbit decays slowly, taking millions or billions of years to change appreciably. But as they get closer, the process accelerates. The waves get stronger, carrying away more energy, shrinking the orbit faster, which makes the waves even stronger in a runaway feedback loop. In the final minutes or hours, the black holes are orbiting each other at a significant fraction of the speed of light, separated by just a few times their event horizon radii. The gravitational waves they're emitting are powerful enough to be detected across the universe. This is what LIGO and Virgo are listening for, these final death spirals of binary black holes. And then, in the final fraction of a second, they merge. The event horizons touch and join, forming a single, larger event horizon. The newly formed black hole oscillates, rings like a bell, radiating away the last asymmetries in gravitational waves, and then it settles, smooth and quiet, into its final state. The whole process, from formation of the binary to final merger, can take billions of years. But we observe the very end, the last few orbits, the merger itself, the ring down, compressed into just a few seconds of data in our detectors. It's like watching a cosmic drama and only seeing the final act, the climax, while the long build-up played out invisibly over cosmic time. Stephen Hawking discovered that black holes aren't entirely black. They emit faint thermal radiation. In 1974, Stephen Hawking made a discovery that surprised everyone, including himself. He was trying to understand what happens to quantum fields near a black hole's event horizon, combining quantum mechanics with general relativity in a way that hadn't been done before. And he found something unexpected. Black holes should glow. Not with reflected light, not with radiation from an accretion disk, but with their own intrinsic thermal radiation arising from quantum effects right at the event horizon. It's called Hawking radiation now, and it's one of the most beautiful and strange predictions in theoretical physics. Here's the idea, simplified. Quantum mechanics allows particle-antiparticle pairs to spontaneously appear and annihilate throughout empty space. Normally, these virtual particles exist for such brief moments that we never notice them. But near a black hole's event horizon, something remarkable can happen. One particle of the pair might fall into the black hole while the other escapes. To a distant observer, it looks like the black hole is emitting particles, like it's radiating. The radiation is thermal, meaning it has a temperature. And astonishingly, that temperature is inversely proportional to the black hole's mass. Larger black holes are colder. Smaller black holes are hotter. A stellar mass black hole would have a temperature of about a millionth of a degree above absolute zero, far colder than the cosmic microwave background, far too cold to detect. But the principle is profound. Black holes aren't eternal. They can evaporate, slowly losing mass through this radiation, gradually shrinking over unimaginable timescales. Hawking radiation is inversely proportional to the black hole's mass, so smaller black holes evaporate faster. There's something almost poetic about how Hawking radiation works. The smaller the black hole, the hotter it glows, and the faster it evaporates. It's a runaway process, a feedback loop that accelerates toward a dramatic end. A stellar mass black hole, say 10 times the sun's mass, would take about 1067 years to evaporate, far, far longer than the current age of the universe, longer than any meaningful timescale in cosmology. For practical purposes, such black holes are essentially eternal on any timescale we care about. But imagine a smaller black hole, maybe one with the mass of a mountain. It would be hotter, glowing more intensely with Hawking radiation. It would evaporate faster, perhaps taking only billions or trillions of years. Smaller still, say, the mass of an asteroid, and the evaporation time drops to thousands or millions of years. And if you somehow had a truly tiny black hole, maybe just a few thousand kilograms, it would be incredibly hot, hotter than any star, radiating furiously. It would evaporate in seconds or less, ending its life in a final burst of energy. The process accelerates because as the black hole loses mass, its temperature increases, which means it radiates more intensely, which means it loses mass faster, which increases the temperature further. The final moments would be explosive, though for stellar mass black holes, those final moments are so far in the future that the universe will have changed beyond recognition before they arrive. A black hole with the mass of a mountain would evaporate in about the age of the universe. Let's play with scales for a moment. Imagine different-sized black holes, and their fates. A mountain mass black hole, say around 10-11 kilograms, about the mass of Mount Everest, would have a temperature of around 10-12 Kelvin. That's incredibly hot, far hotter than any star's core, hot enough to emit gamma rays. Such a black hole would be tiny. Its event horizon would be smaller than a proton, and it would be bright, radiating away its mass energy at a rate that would make it evaporate over a time scale comparable to the current age of the universe, around 10 billion years or so. If such a black hole had formed in the early universe, maybe in the first moments after the Big Bang, when conditions were dense and chaotic enough that black holes of any mass might have formed, it would be reaching the end of its life right around now. It would be in those final stages of runaway evaporation, glowing brilliantly, approaching its explosive end. We've never detected such a black hole, never seen the signature of one evaporating. But that doesn't mean they don't exist. They'd be incredibly small, incredibly rare if they exist at all, and their radiation would be difficult to distinguish from other high-energy astrophysical sources. Still, there's something compelling about the idea that scattered through the universe there might be these tiny, ancient black holes, relics from the beginning of time, now in their final moments, blazing out their existence in bursts of radiation that we've yet to notice. The temperature of Hawking radiation for a stellar mass black hole is incredibly tiny, less than a millionth of a degree above absolute zero. For the black holes we actually observe, the ones formed from collapsing stars, the ones orbiting companion stars, or lurking isolated in the galaxy, Hawking radiation is purely theoretical. Not because it doesn't exist, but because it's far too weak to detect. A black hole with 10 solar masses would have a Hawking temperature of about 6 billionths of a Kelvin. That's not just cold. That's far colder than anything else in the universe. The cosmic microwave background radiation that fills all of space has a temperature of about 2.7 Kelvin. Orders of magnitude hotter than the Hawking radiation from a stellar mass black hole. What this means is that stellar mass black holes are actually absorbing far more radiation from the cosmic microwave background than they're emitting through Hawking radiation. They're gaining mass, not losing it, at least for now. Only in the far future, when the universe has expanded so much that the cosmic microwave background has cooled below the Hawking temperature, will these black holes start to actually evaporate. So Hawking radiation, while fundamentally important for our theoretical understanding, is practically undetectable for real astrophysical black holes. It's a prediction about the deep nature of space-time and quantum fields, about how the universe works at its most fundamental level, but it's not something we can go out and measure with current technology. Sometimes in physics, the most profound truths are also the most subtle, requiring not experiments, but thought, mathematics, the careful application of physical principles to extreme situations to reveal what must be true even if we cannot yet observe it directly. The information paradox asks whether information about matter that falls into a black hole is destroyed forever. Here's one of the deepest puzzles in modern physics, a question that has occupied some of the best minds for decades. What happens to information that falls into a black hole? In quantum mechanics, information is never destroyed. It might be scrambled, made practically impossible to reconstruct, but in principle it's always there. encoded in the quantum state of the system. This is called unitarity, and it's a fundamental principle, one of the bedrock assumptions of how quantum mechanics works. But when something falls into a black hole, it seems to disappear. The no-hair theorem says that the black hole only remembers mass, spin, and charge. All the detailed information about what fell in, its quantum state, its history, everything else, seems to be lost. And if the black hole eventually evaporates through Hawking radiation, and that radiation is purely thermal with no information encoded in it, then the information seems to be gone forever. This contradicts unitarity. It suggests that quantum mechanics breaks down for black holes, or that our understanding of general relativity needs modification, or that something subtle is happening that we haven't figured out yet. Stephen Hawking originally argued that information is indeed destroyed, that black holes represent a genuine exception to quantum mechanics. But this caused such discomfort among physicists that intense effort went into finding ways around it. And gradually, opinion has shifted toward believing that information must be preserved somehow, even if we don't fully understand the mechanism. The paradox remains unresolved, a tension between our best theory of gravity and our best theory of quantum mechanics, a sign that we're missing something deep about how the universe works. Some physicists propose that information is encoded on the event horizon itself, like a cosmic hologram. One of the most intriguing ideas to come out of the information paradox is the holographic principle, the notion that all the information about what falls into a black hole might be encoded on its event horizon, on that two-dimensional surface, rather than in the three-dimensional volume inside. It sounds bizarre, but there are reasons to take it seriously. Jacob Bekenstein showed that a black hole's entropy, a measure of information, is proportional to the area of its event horizon, not its volume. This is strange. Normally, the information content of a region should scale with its volume. But for black holes, it scales with the surface area. This led to the idea that maybe the event horizon is like a hologram, a two-dimensional surface that encodes information about three-dimensional objects. When something falls into a black hole, perhaps the information about it gets imprinted on the horizon in some way we don't fully understand, scrambled and spread out, but not destroyed. And maybe when the black hole evaporates through Hawking radiation, that information gradually comes back out, encoded in subtle correlations in the radiation that we haven't learned how to detect or decode yet. The holographic principle has grown beyond just black holes. Some physicists now wonder if it applies to the universe as a whole, if all the information in our three-dimensional universe might be encoded on some distant two-dimensional boundary. It's a radical thought, suggesting that our reality might be, in some sense, a projection, a shadow of something written on a cosmic surface. Whether it's true or not, it represents physics at its most imaginative, trying to reconcile contradictions by reconsidering basic assumptions about the nature of space, information, and reality itself. Black hole thermodynamics connects gravity, quantum mechanics, and thermodynamics in profound ways. Black holes obey laws that look remarkably similar to the laws of thermodynamics. They have a temperature, the Hawking temperature. They have entropy, proportional to their event horizon area. And there are relationships between these quantities and the black hole's mass and energy that parallel the laws of thermodynamics almost exactly. This is more than just a mathematical curiosity. It suggests a deep connection between gravity, quantum mechanics, and thermodynamics. Three pillars of physics that we usually think of as separate. Black holes seem to be telling us that they're all aspects of something more fundamental. For instance, when you add mass to a black hole, its event horizon area increases, which means its entropy increases. This is like the second law of thermodynamics, which says that entropy always increases in isolated systems. In fact, if you include black hole entropy in your calculations, you can preserve the second law even when things fall into black holes, something that seemed impossible before Bekenstein's work. And the fact that black holes have temperature means they can be in thermal equilibrium with their surroundings, exchanging energy with the outside universe through Hawking radiation. They're thermodynamic objects, not just gravitational ones. All of this suggests that entropy and temperature aren't just properties of matter, they're properties of space-time itself. The event horizon area representing entropy hints that space-time might have some kind of microscopic structure, some underlying degrees of freedom that we haven't directly observed, but which manifest as the macroscopic properties of black holes. It's one of those areas where physics feels on the verge of a breakthrough, where different theories are brushing up against each other, suggesting connections that we're still learning to articulate fully. The Bekenstein bound limits how much information can be contained in a given region of space. Jacob Bekenstein didn't just work out black hole entropy. He also discovered something more general, a fundamental limit on how much information can be stored in any region of space. It's called the Bekenstein bound, and it says that the maximum entropy, maximum information, that can fit in a spherical region is proportional to the energy in that region times the radius, divided by fundamental constants. For ordinary objects, this bound is absurdly high, way more information than we could ever practically store. But the remarkable thing is that black holes saturate this bound. They achieve the maximum possible information density. A black hole of a given radius contains exactly the maximum amount of information that could possibly fit in that space. This suggests that black holes are, in some sense, the most efficient information storage devices possible. You can't pack more information into a region of space without making a black hole. And once you've made a black hole, you've hit the fundamental limit. The Bekenstein bound has implications beyond black holes. It suggests that there's something fundamental about the relationship between information and space, that you can't arbitrarily concentrate information without bound, that there are physical limits written into the structure of the universe itself. It's another hint that information might be more fundamental than we usually think, not just a convenient concept for describing systems, but something that plays a basic role in the laws of physics, something that space and time and energy are organized around. These ideas are still being explored, still being refined, but they point toward a future understanding of physics where information theory plays as central a role as energy or momentum do in our current theories. Some theories suggest black holes might be connected to white holes, hypothetical objects that expel matter instead of consuming it. White holes are strange beasts, allowed by Einstein's equations, but possibly not existing in nature. They're the time reverse of black holes. Instead of an event horizon that nothing can escape from, they'd have an event horizon that nothing can enter. Matter and light would flow out of them, expelled into the universe, but nothing could fall in. The mathematics of general relativity treats time symmetrically in many ways. If black holes are solutions where matter flows inward, why not solutions where matter flows outward? And indeed, the equations allow for them, these white holes sitting at the other end of some kind of space-time tunnel. Some early speculations suggested that black holes and white holes might be connected by wormholes, Einstein-Rosen bridges, so that what falls into a black hole might emerge from a white hole somewhere else, or someone else. It's a compelling idea, almost science-fictional in its audacity. But white holes face serious problems. They're gravitationally repulsive in a sense, which makes them unstable. Any small amount of matter or radiation from the outside would disrupt them, collapse them, turn them into something else. And we've never observed anything that looks like a white hole. No mysterious sources of matter and energy appearing from nowhere. Most physicists now think white holes don't exist in our universe, that the time symmetry that allows them in the equations is broken by the actual evolution of the cosmos, by the increase of entropy, by the arrow of time. But they remain interesting as thought experiments, as mathematical curiosities, as reminders that the equations sometimes allow possibilities that nature chooses not to actualize. The firewall paradox suggests that quantum effects might create a violent wall of energy at the event horizon. Just when physicists thought they had a handle on the information paradox, with ideas like the holographic principle offering potential solutions, a new puzzle emerged in 2012, called the firewall paradox. The argument goes like this. For information to escape from a black hole through Hawking radiation, the radiation particles must be entangled with particles inside the black hole. But quantum mechanics says that a particle can only be maximally entangled with one other particle. If the Hawking radiation is entangled with particles inside, it can't also be entangled with earlier Hawking radiation that's already escaped. Breaking these entanglements would require energy, enormous amounts of energy, concentrated at the event horizon. This would create a firewall, a wall of incredibly high energy radiation sitting right at the horizon. And that contradicts general relativity, which says that someone falling through the horizon shouldn't feel anything special at that exact location, that the equivalence principle should hold. So we have three principles that can't all be true simultaneously. Unitarity, information is preserved. The equivalence principle, no firewall at the horizon. And standard semi-classical physics, our usual way of combining quantum mechanics and gravity. Something has to give, but we're not sure what. The firewall paradox has sparked intense debate and much creative theorizing. Maybe the equivalence principle breaks down near horizons in subtle ways. Maybe quantum mechanics needs modification. Maybe our understanding of entanglement is incomplete. Or maybe there's a clever way out that we haven't thought of yet. These paradoxes aren't failures of physics. They're opportunities, signs that we're pushing into territory where our current theories need extension or revision. They're the universe's way of saying, keep thinking, you're not done yet. There's more to understand. Black holes play a crucial role in galaxy formation and evolution through their feedback effects. It seems almost impossible that something so small, relatively speaking, could influence something as vast as an entire galaxy. And yet, black holes do exactly that. Their influence extends far beyond their immediate gravitational reach, shaping the very galaxies they inhabit. When a supermassive black hole feeds actively, the energy it releases can heat gas throughout the galaxy. This heated gas becomes too energetic to collapse and form new stars. In essence, the black hole acts as a thermostat, regulating star formation across the entire galaxy. Without this feedback, galaxies would continue forming stars until they exhausted all their gas, becoming far more massive and star-filled than what we actually observe. The jets and winds driven by black hole accretion can also physically push gas out of galaxies, removing the raw material for star formation entirely. In the most massive elliptical galaxies, those giant red H systems with little ongoing star formation, we see clear evidence of this black hole feedback. Cavities in the hot gas surrounding these galaxies, blown out by jets from the central black hole, mark where energy has been deposited over millions of years. So in a strange way, black holes create darkness, not just through their gravity, but through their influence on star formation. They prevent stars from forming, keeping galaxies dimmer than they would otherwise be. The darkest objects in the universe help determine where light appears and where it doesn't. It's a cosmic balance, a regulatory system operating on the largest scales, governed by objects that are themselves incredibly compact. The universe, it seems, uses black holes as tools of organization, as sculptors that shape the distribution of matter and light across cosmic time. Tidal disruption events occur when a star wanders too close to a supermassive black hole and is torn apart. Most stars orbit safely in their galaxies, never getting close enough to the central supermassive black hole to be in danger. But occasionally, perhaps once every 10,000 years per galaxy, a star's orbit brings it too close. And when that happens, the tidal forces become strong enough to overcome the star's own gravity, and the star is ripped apart. This is called a tidal disruption event, and it's one of the most violent fates a star can meet. The tidal forces, the difference in gravitational pull between the near side and far side of the star, stretch it into a long stream of gas. Part of that stream gets flung away at high speed, escaping the black hole entirely. The rest remains gravitationally bound, spiraling back around to form an accretion disk. For a few months or years, the black hole suddenly has a fresh supply of stellar material to feed on. The accretion disk brightens dramatically, sometimes by factors of thousands or more, as the disrupted star's gas heats up and radiates. The black hole, previously quiet or dim, becomes temporarily bright, a flare visible across millions of light years. From our perspective as observers, these events are fascinating laboratories. We can watch in real time as a star is destroyed and consumed, seeing the black hole's feeding behavior, studying how matter accretes and radiates in these extreme conditions. Each event is slightly different stellar masses, different orbital geometries, different black hole properties, giving us a range of scenarios to analyze. There's something poignant about these events too. Stars that have shone for millions or billions of years, suddenly encountering the wrong part of space at the wrong time and being torn apart in a matter of hours. It's a reminder that even in the relative emptiness of space, there are places where getting too close means destruction, where curiosity or chance can lead to violent endings. Astronomers observe tidal disruption events as sudden brightening in the centers of distant galaxies. One of the ways we've learned about tidal disruption events is through surveys that repeatedly observe the same patches of sky, looking for things that change. Most galaxies stay about the same brightness night after night, year after year. But occasionally, one will suddenly brighten, not from a supernova, which has its own characteristic light curve and spectrum, but from the center, from the nucleus. When astronomers see this signature brightening in a galaxy's core, they investigate. They take spectra, measuring the light's composition and properties. They monitor the brightness over time, watching how it evolves. And sometimes the evidence points to a tidal disruption event, a star being destroyed and consumed by the central black hole. The light curves of these events have characteristic shapes. There's a rapid rise as the stream of disrupted stellar material first falls back and begins accreting, then a gradual decline, following a predictable power law as the supply of infalling material gradually exhausts itself. The whole process might take months or years, depending on the specifics of the disruption. Different wavelengths tell different parts of the story. Optical and ultraviolet light trace the accretion disk's emission. X-rays might reveal corona around the disk, regions of even hotter plasma. Radio emissions can indicate jets or outflows launched during the event. Each tidal disruption event we observe adds to our statistical understanding. How common are they? Do they depend on black hole mass or galaxy type? Do jets form in some events but not others? Can we use them to find otherwise invisible black holes in galaxy centers? These are active areas of research, using stellar destruction as a probe of black hole properties and behaviors. The microquasar SS433 contains a black hole that launches jets of material at about 1/4 the speed of light. SS433 is one of the stranger objects in our galaxy. A microquasar, a stellar mass black hole that mimics on a small scale what supermassive black holes do in active galactic nuclei. It's in a binary system, pulling material from a companion star, and from that accretion it launches jets. But these jets have a unique property. They're precessing, wobbling like a tilted spinning top. The jets shoot out at about 26% of the speed of light, relativistic speeds that smear out spectral lines through Doppler shifting. But because the jets are precessing with a period of about 162 days, those Doppler shifts change over time, creating a distinctive pattern in the spectrum. The spectral lines sweep back and forth in wavelength as the jets sweep around in space. It's like watching a cosmic sprinkler, jets of matter spinning around as they spray outward. The precession might be caused by the accretion disk itself being warped or tilted relative to the black hole's spin axis, creating a situation where torques from the inner and outer disk compete, causing the whole system to wobble. SS433 has been studied for decades, and it remains a Rosetta Stone for understanding jet formation and relativistic outflows. It's close enough and bright enough that we can observe it in detail, measuring properties that are harder to access in more distant or powerful systems. And there's something almost whimsical about its behavior, the regular precession, the predictable pattern, like a cosmic clock or a lighthouse with a bent beam. The universe occasionally creates systems that are not just violent or extreme, but also somehow choreographed, following patterns that we can track and predict, finding order in the chaos. Black holes can act as gravitational lenses, bending light from objects behind them. Gravitational lensing is one of the predictions of general relativity that continues to amaze me. The idea that massive objects don't just pull on matter, but bend the path of light itself, or more accurately, curve the space-time through which light travels. Black holes, being extremely massive and compact, are particularly effective gravitational lenses. Light passing near a black hole gets deflected, bent around it, creating multiple images of background objects, or sometimes complete rings of light, Einstein rings, if the alignment is just right. This lensing effect can actually help us detect black holes that are otherwise invisible. If a black hole passes between us and a more distant star, the star's light will be magnified and its image distorted in a characteristic way. By monitoring how the brightness and position of the background star changes over time, astronomers can infer the presence and mass of the foreground black hole. There's also something called microlensing, when the lensing object is small, like a stellar mass black hole, creating brief brightening events as it passes in front of background stars. Several projects monitor millions of stars looking for these events, and some of them might be caused by isolated black holes drifting through our galaxy. The lensing around supermassive black holes creates those beautiful images we've seen from the Event Horizon Telescope, the bright ring of light surrounding the dark shadow. That ring is partly due to lensing, to light from the accretion disk being bent around the black hole by its extreme gravity, creating a luminous halo that defines the shadow's edge. Gravity as a lens, it's such an elegant concept, and it turns invisible objects into detectable ones, allowing us to map the distribution of dark matter and dark objects throughout the universe. The Milky Way probably contains tens of millions of stellar mass black holes, quietly drifting through space. When we talk about black holes, we often focus on the dramatic ones, the ones with accretion disks, the ones in binary systems pulling material from companion stars, the ones that are bright and active and easy to spot. But most black holes are probably none of those things. For every stellar mass black hole we've detected, there are probably thousands or tens of thousands more that are isolated, dark, silent. They formed from massive stars that went supernova, but they were born alone, or their companions were disrupted during the supernova. And now they drift through the galaxy, invisible and undetectable, except through their gravitational influence. Based on our understanding of stellar evolution and supernova rates, astronomers estimate that the Milky Way might contain somewhere between 10 million and 100 million stellar mass black holes. But we've only confirmed the existence of a few dozen. The vast majority are completely unknown to us, dark wanderers moving through the spaces between stars. Occasionally, one of these isolated black holes might pass through a cloud of gas and briefly accrete some material, flaring up for a time before fading back into invisibility. Or it might gravitationally lens a background star, creating a brief microlensing event. But mostly, they're just there, massive but unobtrusive, part of the galaxy's unseen population. It's a humbling thought that our galaxy is home to millions of these objects, and we're only just beginning to census them, to understand their distribution and properties. The universe we can see is just a small fraction of what's actually there, and the darkness hides more than we've yet learned to reveal. Hypervelocity stars racing out of the galaxy at incredible speeds may have been flung by interactions with our central black hole. Most stars in the galaxy have reasonably sedate motions, orbiting the galactic center at speeds of a few hundred kilometers per second. But occasionally, astronomers find stars moving much faster, at speeds of 500, 700, even over 1,000 kilometers per second, fast enough to escape the galaxy's gravity entirely, to be ejected into intergalactic space. These are called hypervelocity stars, and one mechanism that can produce them involves the supermassive black hole at the galaxy's center. Imagine a binary star system, two stars orbiting each other, that wanders too close to Sagittarius A. The black hole's gravity can disrupt the binary in a process called tidal capture. One star gets captured into orbit around the black hole, while its companion gets flung away at tremendous speed, like a slingshot effect. The captured star might eventually be consumed or disrupted itself, but the ejected star is now racing outward through the galaxy at escape velocity. Over millions of years, it will leave the Milky Way entirely, becoming an intergalactic wanderer, a star without a galaxy. We've found several dozen hypervelocity stars. So far, and by tracing their orbits backward, many seem to originate from the galactic center. They're like messengers from the heart of the galaxy, carrying information about the environment near the central black hole, showing us the violence that can occur in those dense central regions. There's something lonesome about these stars, exiled from their home galaxy, destined to wander the void between galaxies forever. But they're also freed in a way, no longer bound by the galaxy's gravity, able to explore regions of space that most stars will never see. Perhaps destruction and liberation are sometimes just different perspectives on the same event. Some galaxies lack a central, supermassive black hole, suggesting diverse formation histories. While nearly all large galaxies seem to have supermassive black holes at their centers, there are exceptions. Galaxies where careful searches find no evidence of a central black hole, or where any black hole that exists must be much smaller than expected. These exceptions are fascinating because they suggest that the relationship between galaxies and black holes, while strong, isn't universal. Perhaps these galaxies formed under different conditions, or perhaps they lost their central black holes through some process, maybe a gravitational wave recoil event where a merged black hole was kicked out of the galaxy entirely. Some dwarf galaxies seem to lack massive black holes, which makes sense. They're small, formed from less material, and might never have had the conditions to grow a large central black hole. But finding even a few larger galaxies without them challenges our understanding of coevolution, suggesting that the pathways to galaxy formation are more diverse than we thought. It's also possible that some of these galaxies do have central black holes, but they're so quiet, accreting so little material, that we simply can't detect them yet. The absence of evidence isn't always evidence of absence. But as our observations improve, as we develop better techniques for detecting dormant black holes, we'll get a clearer picture of which galaxies truly lack them and which are just hiding them well. These outliers are important. They define the boundaries of what's normal, help us understand what's necessary for black hole formation and what's contingent, what patterns are universal laws, and what are just common outcomes. The exceptions teach us as much as the rules. The density of a supermassive black hole can be less than water when averaged over its volume. Here's a counterintuitive fact that often surprises people. If you calculate the average density of a supermassive black hole by dividing its mass by the volume enclosed by its event horizon, you get a number that's surprisingly small, sometimes less than the density of water, even less than the density of air. This isn't because the singularity at the center isn't dense. It presumably is, infinitely so, according to classical general relativity. Rather, it's because the event horizon grows faster than the mass as black holes get larger. The radius of the event horizon is proportional to the black hole's mass, so the volume, which goes as radius cubed, grows as the cube of the mass. Meanwhile, the mass only grows linearly. So average density decreases as black holes get more massive. For a stellar mass black hole, the average density is still enormous, nuclear densities or higher. But for a supermassive black hole with billions of solar masses, the event horizon is so large compared to the mass that the average density drops to ordinary, even mundane values. This doesn't mean you could survive inside such a black hole. The tidal forces near the singularity would still destroy you, and you'd be trapped with no way out. But it does mean that crossing the event horizon of a supermassive black hole might be less immediately violent than crossing that of a smaller one. That you'd have more time inside before the singularity's influence became overwhelming. It's one of those facts that reminds us that intuition developed in ordinary environments doesn't always serve us well in extreme ones. That the universe is full of situations where the obvious expectation turns out to be wrong in interesting ways. In higher dimensional theories of physics, black holes might have very different properties. Our universe appears to have 3 dimensions of space and 1 of time. But some theoretical frameworks, string theory in particular, suggest that there might be additional spatial dimensions, hidden from us because they're curled up at incredibly tiny scales, far smaller than anything we can directly observe. If these extra dimensions exist, black holes might behave differently than they do in our familiar 4-dimensional space-time. In higher dimensions, the mathematics of gravity changes. The event horizon would have different geometry. The strength of gravitational forces would fall off at different rates with distance, and the properties of Hawking radiation might be altered. Some string theory scenarios suggest that if these extra dimensions become accessible at high enough energies that might be reached in particle colliders or in the early universe, we might be able to create or detect microscopic, higher dimensional black holes. These would evaporate almost instantly through Hawking radiation, but their brief existence might leave detectable signatures. The shape of a black hole's event horizon also changes with dimensionality. In 3 spatial dimensions, it's a sphere. In 4 spatial dimensions, it would be a 3-dimensional hypersphere. The mathematics gets more complex, but also reveals new possibilities, black hole solutions that don't exist in lower dimensions, instabilities that appear in higher dimensional gravity. These are deeply speculative ideas, and we have no direct evidence that extra dimensions exist, but they represent physics at its most exploratory, asking what if, playing with the mathematics, seeing where the logic leads. Sometimes these explorations reveal unexpected connections or solve existing problems. Other times, they simply expand our sense of what's possible, what forms reality might take in different configurations. Primordial black holes might have formed in the first moments after the Big Bang from density fluctuations. Not all black holes need to form from stars. In the first fraction of a second after the Big Bang, the universe was incredibly dense and chaotic, with quantum fluctuations creating regions of higher and lower density. If some of those overdense regions were sufficiently compressed, they might have collapsed directly into black holes. Primordial black holes, formed not from stellar death, but from the extreme conditions of the early universe. These primordial black holes could have a wide range of masses, from microscopic, perhaps as small as the Planck mass, about 10^8 kilograms, all the way up to thousands of solar masses, depending on the size and timing of the density fluctuation that formed them. The smallest ones would have evaporated long ago through Hawking radiation, disappearing in bursts of energy. But larger ones, those with masses above, say 10 or 11 kilograms, would still exist today, scattered throughout the universe, relics from the very beginning of time. We've never definitively detected a primordial black hole, but that doesn't mean they don't exist. They'd be difficult to spot, isolated, dark, not accreting material, invisible except through their gravitational effects. Some searches look for their gravitational lensing signatures, brief brightenings of background stars, as a primordial black hole passes between us and them. If they exist in sufficient numbers, primordial black holes might even account for some or all of dark matter, the mysterious invisible mass that makes up most of the matter in the universe. It's a speculative idea, and most dark matter is probably something else, exotic particles we haven't discovered yet. But primordial black holes remain a possibility, a candidate that hasn't been ruled out. Some cosmologists propose that primordial black holes could account for some or all of dark matter. Dark matter is one of the great mysteries of modern cosmology. We know it exists. Its gravitational effects are visible in galactic rotation curves, in the motion of galaxy clusters, in the patterns of cosmic microwave background radiation. But we don't know what it is. Decades of searches for exotic particles, WIMPs, axions, sterile neutrinos, have come up empty so far, which brings us back to an old idea. What if dark matter isn't exotic particles at all, but ordinary matter locked in compact objects we can't see? Specifically, what if it's primordial black holes? There are constraints on this idea. Black holes in certain mass ranges would have detectable effects that we don't observe. Very small ones would have evaporated. Intermediate ones would gravitationally lens background stars at rates we don't see. Very large ones would disrupt stellar systems in ways that don't match observations. But there are still windows, particular mass ranges where primordial black holes could exist in sufficient numbers to account for dark matter without contradicting observations. Maybe around 10^11 to 10^8 solar masses, or around 1 to 100 solar masses, though these windows keep getting narrower as observations improve. Recent gravitational wave detections have shown that stellar mass black holes are more common than we thought, and some of the merging black holes have properties that are hard to explain with standard stellar evolution. Could some of them be primordial black holes instead? It's possible, though far from proven. The idea is appealing in some ways. It would solve the dark matter mystery using physics we already understand, rather than requiring new particles. But nature doesn't always choose the path we find most appealing. Whether primordial black holes make up any significant fraction of dark matter remains an open question, one that observers are actively working to answer. Micro-black holes, if they exist, could be created in particle accelerators or cosmic ray collisions. Some extensions of physics predict that if extra dimensions exist and are accessible at TeV energy scales, energies reachable in modern particle accelerators like the Large Hadron Collider, then it might be possible to create tiny, microscopic black holes in high-energy collisions. This sounds alarming at first. Creating black holes on Earth? Won't they grow and consume everything? But Hawking radiation saves us. A micro-black hole with a mass of, say, 10 or 24 kilograms would have a temperature of about 1029 Kelvin and would evaporate in about 10 nor 96 seconds. Essentially instantaneously, it would decay into a shower of ordinary particles before it could interact with anything or accrete even a single atom. Despite much searching, no evidence of micro-black hole creation has been found in collider experiments. This doesn't mean the theories are wrong. It might just mean the energy scales required are higher than we can reach, or that the extra dimensions don't exist, or that they're configured differently than the simplest models suggest. Similar micro-black holes might also form when ultra-high energy cosmic rays, particles from space moving at nearly the speed of light, collide with particles in Earth's atmosphere. If they do, they evaporate instantly, and we might detect their decay products as unusual patterns in cosmic ray showers. The search for micro-black holes is part of the larger search for physics beyond the standard model, for evidence of extra dimensions, quantum gravity effects, or new fundamental forces. Each negative result tells us something, sets limits on theories, narrows the possibilities, guides theorists toward more accurate models of how the universe works at its smallest scales. The cosmic censorship hypothesis suggests that singularities always hide behind event horizons. Roger Penrose proposed what he called the cosmic censorship hypothesis, the idea that nature abhors naked singularities, singularities that aren't hidden behind event horizons, that are visible to the outside universe. Why would this matter? Because singularities are places where physics breaks down, where our equations give infinite answers and stop making sense. If a naked singularity existed, we could observe it, and all our ability to predict the future would fail. Information could appear from the singularity unpredictably, violating the determinism that underlies most of physics. Event horizons act as a kind of censorship, hiding the singularity from view, ensuring that the breakdown of physics remains hidden where it can't affect the outside universe. We can't see what happens at the singularity, can't probe it with light or any other signal, and so the madness stays contained. The hypothesis comes in two forms. Weak cosmic censorship says that singularities that form from reasonable initial conditions are always hidden. Strong cosmic censorship says that the universe is deterministic, that what we can observe now fully determines what will happen in the future, with no unpredictable influences from hidden regions. We have no proof that cosmic censorship is true. It remains a conjecture, and mathematicians have found exotic solutions to Einstein's equations that might violate it. But most physicists suspect it holds in our universe, that nature has found a way to quarantine the places where physics fails, to keep the universe predictable and comprehensible even when it contains singularities. It's a kind of mercy, in a way, the universe protecting us from seeing its own limitations, its own boundaries of sensibility. Naked singularities, singularities without event horizons, would allow us to observe regions where physics fails. If cosmic censorship is violated, if naked singularities can exist, then we face a strange situation. We could observe objects where the laws of physics as we know them cease to function, where equations give meaningless answers, where anything might happen. Some exotic solutions to Einstein's equations do allow naked singularities. Rapidly rotating black holes, if spun up past the extremal limit, would develop naked singularities. Collapsing objects with certain strange mass distributions might form them. But each time someone finds such a solution, the question becomes, could this actually occur in nature? Or is it a mathematical curiosity that requires such fine-tuned conditions that the universe never realizes it? Most physicists lean toward believing naked singularities don't exist in our universe. Every time we've observed black hole candidates, they behave as if they have event horizons. The gravitational wave observations showed the characteristic ring down of black holes settling into their final states, consistent with event horizons existing. But we can't rule them out completely, not yet. And if one did exist, if we could observe a naked singularity, what would we see? Unpredictable behavior, perhaps? Physics that doesn't follow the usual rules? A place from which information could emerge without cause, violating our expectations about causality and determinism. It would be fascinating and terrifying in equal measure. A window into the limits of physical law, a place where the universe admits that our descriptions are incomplete, that there are realms beyond current understanding. Most likely, though, nature has closed that window, hidden those places behind horizons, kept the universe comprehensible even at its most extreme. Loop quantum gravity suggests that the singularity inside a black hole might be replaced by a quantum bounce. General relativity predicts that black holes contain singularities, points of infinite density where physics breaks down. But many physicists suspect this is a sign that general relativity is incomplete, that quantum effects must take over before the singularity is reached. Loop quantum gravity is one attempt to quantize gravity, to merge general relativity with quantum mechanics. In this framework, space itself is made of discrete, quantized loops at the Planck scale, the smallest meaningful length, about 10⁻35 meters. Space is grainy rather than smooth at the tiniest scales. When you apply loop quantum gravity to black holes, something interesting happens. The singularity might be avoided entirely. Instead of collapsing to infinite density, the matter reaches a maximum density, enormous, but finite, and then bounces. The collapse reverses, and the matter begins expanding again. Where does it expand to? Some models suggest it could create a new region of space-time, perhaps even a new universe, connected to our space-time through the black hole's interior. The black hole in our universe would be a white hole in that other universe, and the Big Bang of that universe would be the bounce from the black hole collapse in ours. It's highly speculative, and we have no way to test it directly. We can't look inside black holes to see what actually happens. But it represents one possibility for resolving the singularity problem, for showing that quantum effects might smooth out infinities, that the universe might avoid true breakdowns even in the most extreme conditions. The mathematics is complicated, the predictions are difficult to extract, but the basic idea is appealing, that there are no true singularities, no places where physics genuinely fails, just transitions to regimes where our current descriptions need refinement. Some speculative theories propose that our entire universe might exist inside a black hole. Here's a wild thought, more philosophical than scientific but mathematically interesting. What if our universe, everything we observe, the Big Bang itself, is the interior of a black hole in some larger parent universe? The idea comes from noticing certain mathematical similarities between the Big Bang space-time and the interior of a black hole. Both have singularities in their past, the Big Bang singularity and the black hole's central singularity. Both have expanding space. Inside a black hole, space expands in the direction toward the singularity, similar to how our universe expands in time from the Big Bang. If this were true, it would mean that every black hole we observe might contain an entire universe, with its own galaxies, stars, perhaps even life, all trapped inside an event horizon, unreachable and unknowable from our perspective. And our universe in turn would be trapped inside a black hole in some larger cosmos. It's an idea that multiplies realities, that suggests the universe has layers and depths we can never directly access. There's no way to test it. We can't look outside our universe to see if we're inside a black hole, and we can't look inside black holes to see if they contain universes. It remains speculation, a thought experiment rather than a scientific hypothesis. But it captures something about the human imagination, our tendency to wonder if there's more beyond what we can see, if the boundaries we encounter might also be doorways to other realms. Black holes might serve as natural laboratories for studying quantum gravity. We need a theory of quantum gravity, a framework that successfully combines general relativity's description of space-time with quantum mechanics' description of particles and fields. This is one of the great unsolved problems in physics, and we don't yet have experimental guidance to point the way. But black holes might help. They're places where both quantum mechanics and general relativity are crucial, where neither can be ignored. At the event horizon, quantum effects create Hawking radiation. Near the singularity, quantum effects should become important in determining space-time's structure. Black holes are where the two theories meet, where they must somehow work together. Many of the puzzles we've discussed, the information paradox, black hole thermodynamics, the nature of singularities, require quantum gravity to fully resolve. Each puzzle is a clue, a constraint that any successful theory must satisfy. If we can understand black holes deeply enough, we might be able to work backward to the underlying theory. Gravitational wave observations, detailed studies of black hole shadows, measurements of Hawking radiation if we can ever detect it. All of these could potentially reveal deviations from classical general relativity, hints of quantum effects in strong gravity. Each observation refines our understanding, rules out some theories, and constrains others. In this way, black holes are gifts to theoretical physics, natural experiments at energy scales and curvatures we could never reproduce artificially, testing grounds for our most fundamental ideas. We can't create quantum gravity conditions in a laboratory, but the universe has created them for us in black holes, and we can observe them from afar, learning from what we see. The fuzzball proposal suggests that the entire black hole interior is a quantum superposition of string states. String theory offers another perspective on black holes, another way of thinking about what they might actually be at the quantum level. In the fuzzball proposal, a black hole isn't a classical object with an event horizon surrounding empty space and a central singularity. Instead, the entire region that we think of as the black hole interior is filled with a complex quantum sum superposition of string states. Strings are the fundamental objects in string theory, one-dimensional entities that can vibrate in different modes, with each mode corresponding to a different particle. The fuzzball idea is that what we perceive as a black hole is actually an incredibly complex tangle of strings, filling the whole volume up to where we see the event horizon. The horizon itself isn't a sharp boundary, but an effective description that emerges from the quantum fuzzball. In this picture, there's no singularity at the center because the center isn't empty. It's full of strings in complicated quantum states. Information that falls in gets scrambled and encoded in these string states, but it's not destroyed. It remains there, in the quantum configuration of the fuzzball, potentially recoverable in principle, even if impossible in practice. The mathematics is extremely complex, and the proposal is still being developed and debated. But it represents one possible resolution to the information paradox and the singularity problem, replacing classical geometry with quantum states, showing that what appears to be empty space and infinite density is actually a complex quantum system that we're just describing approximately with classical concepts. Whether fuzzballs are the right description or not, they show how different physics might look at the quantum level, how objects we think of as simple and geometric might actually be rich with quantum structure that we're only beginning to understand. We don't know if the singularity is a point, a ring, or something else entirely. For a non-rotating black hole, a Schwarzschild black hole, the mathematics suggests the singularity is a point, a zero-dimensional location where all the mass is concentrated and density becomes infinite. But for a rotating black hole, a Kerr black hole, which is probably more realistic since most astrophysical objects spin, the mathematics describes something different, a ring singularity. This ring sits in the equatorial plane of the black hole, spinning with it. It's not a physical ring of matter, but a ring-shaped region in space-time where the equations break down, where curvature becomes infinite. The geometry becomes so strange that paths can pass through the ring, potentially leading to other regions of space-time. Though these are likely mathematical artifacts rather than actual traversable pathways. But here's the uncertainty. These descriptions come from classical general relativity, which we know is incomplete. When quantum effects are included, and they must be, at the Planck scale where these singularities exist, the picture almost certainly changes. The singularity might be replaced by something else, a finite but extremely dense core, a quantum foam of fluctuating space-time, a region where space and time lose their usual meanings entirely. We simply don't know. The singularity is hidden behind the event horizon, permanently out of reach of our observations. We can't probe it with instruments, can't verify what's actually there. Our best theories predict something that they also tell us they can't accurately describe. It's a kind of fundamental ignorance built into the structure of the universe, a place where certainty ends and mystery persists. And perhaps that's appropriate. Perhaps reality reserves the right to have aspects that remain forever beyond our direct observation, knowable only through their indirect effects on the universe we can see. The black hole complementarity principle suggests that reality might be fundamentally observer-dependent. The information paradox led to a radical proposal called black hole complementarity, suggested by Leonard Susskind and others. It says that there isn't one single objective description of what happens to matter falling into a black hole. Rather, the description depends on who's observing. For an observer falling into the black hole, they pass smoothly through the event horizon, carrying their information with them into the interior. From their perspective, the information crosses the horizon and reaches the singularity, or whatever replaces it. But for an observer staying outside, the information never crosses the horizon. Instead, it gets scrambled and spread across the horizon surface, eventually being re-emitted in Hawking radiation over incredibly long timescales. From this perspective, the information stays outside, gets thermalized, and comes back out. Both descriptions are supposedly correct, even though they seem contradictory. The key is that no single observer can verify both. The infalling observer can't report back to the outside observer what they experienced, and the outside observer can't see what happens inside the horizon. So there's no observable contradiction, even though the two stories seem incompatible. This is deeply strange. It suggests that reality itself might not have a single, objective description, that what happens depends on your frame of reference in a more profound way than even special relativity suggests. It's not just that different observers measure different times and distances. It's that the very sequence of events, what happens to information, might be observer-dependent. Black holes challenge our understanding of causality, time, and the nature of reality itself. Inside a black hole's event horizon, space and time swap roles in a sense. Outside, you can move freely through space but only forward in time. Inside, you're pulled inexorably toward the singularity, not through space exactly, but through time. The singularity isn't a place you move toward spatially. It's a moment in your future that you can't avoid, like next Tuesday is unavoidable for us. This strange reversal challenges our intuitive understanding of causality. Cause and effect, which we usually think of as temporal relations, causes precede effects in time, becomes spatially oriented inside the horizon. Every path through time leads to the singularity. You can delay it by firing rockets, just as you can delay arriving at a spatial destination, but you can't avoid it, just as we can't avoid moving forward in time. The event horizon itself is a null surface, a boundary in space-time that light rays can trace but never cross outward. It's less like a physical barrier and more like a point of no return in the causal structure of space-time itself. Once you're there, all your possible futures lie inside, none outside. These aren't just mathematical curiosities. They represent genuine challenges to our conceptual framework, to how we think about time, space, and causality. Black holes force us to reconsider whether time is truly fundamental or emergent, whether causality is as straightforward as it seems, whether our universe's structure allows for absolute determinism, or whether some futures are genuinely open while others are closed. Every black hole is a philosophical problem dressed in mathematics, a question about the nature of existence that we can't fully answer yet. Some physicists wonder whether consciousness could survive falling into a black hole in any meaningful sense. This is more philosophical than physical, but it's a question that naturally arises. What would it be like to fall into a black hole? Not just physically, but experientially. Would consciousness persist? Would there be a subjective experience of crossing the horizon and approaching the singularity? From a physical standpoint, for a large enough black hole, your brain would continue functioning for some time after crossing the horizon. The neural signals, the electrochemical processes that give rise to consciousness, all of that would continue, at least until tidal forces became strong enough to disrupt biological structures. But information about your experiences couldn't escape. Your consciousness would be isolated, cut off from the rest of the universe with no possibility of communication. Any thoughts you had, any experiences you processed, would be yours alone, forever unshared. And as you approach the singularity, as space-time curvature became extreme, would there be a point where consciousness itself breaks down? Not because the neurons stop firing, but because the very structure of space and time becomes so distorted that the concept of sequential thoughts, of a continuing stream of awareness, stops making sense. These are unanswerable questions, at least empirically. No observer can fall in and report back, but they touch on deep issues about the relationship between consciousness and the physical universe, about whether subjective experience depends on particular space-time structures, about what it means to exist in a place where the normal rules are suspended. Perhaps consciousness, like information, is preserved in some way we don't understand. Or perhaps it truly ends at the singularity, a final cessation that we can't observe but can imagine. The ultimate fate of black holes depends on whether Hawking radiation truly causes them to evaporate completely. If Hawking radiation is real, and most physicists believe it is, then black holes aren't eternal. They evaporate, slowly losing mass, eventually disappearing. But this raises questions about the far future, about what happens to the universe on timescales vastly longer than its current age. In the extremely distant future, 100 years from now, give or take, all the stars will have burned out. Galaxies will have dispersed. Even protons might have decayed, if some theories are right. The universe will be dark, cold, approaching absolute zero, with nothing but black holes remaining as the last reservoirs of organized mass energy. And then slowly, over timescales of 1067 years for stellar mass black holes, and 10100 or even 10106 years for the largest supermassive black holes, even they would evaporate. Each one gradually radiating away its mass, shrinking, heating up, until in a final burst of radiation it disappears entirely. What's left after that? Perhaps just radiation, photons and particles spreading through an ever-expanding space, growing ever more diffuse and cold. The universe approaching a state of maximum entropy, a heat death where nothing interesting can ever happen again, because there are no gradients, no concentrations of energy to drive change. Or perhaps something else. Cyclic models where the universe rebounds, quantum fluctuations that create new structures, possibilities we haven't imagined. But if Hawking radiation is correct, and nothing prevents complete evaporation, black holes are temporary, lasting far longer than stars, but still finite in their existence. They're the longest-lasting objects we know of, the final chapter before the story ends. And in their eventual disappearance, they'd be returning to the universe all the mass and energy they've consumed over cosmic history, making one last contribution before fading away. A black hole's entropy is proportional to its surface area, suggesting that space itself might be quantized. The Bekenstein-Hawking entropy formula says that a black hole's entropy is proportional to the area of its event horizon, divided by the Planck area. This simple relationship has profound implications. Entropy is related to information, specifically to the number of possible microstates that correspond to the same macroscopic state. For a black hole to have entropy proportional to its surface area, there must be microstates associated with that surface. Each Planck area-sized patch on the event horizon must correspond to some fundamental degree of freedom, some quantum bit of information. This suggests that space-time isn't infinitely divisible, that at the Planck scale, about 10^35 meters, space itself becomes grainy, quantized into discrete units. Each patch represents a fundamental pixel of reality, a smallest meaningful region. Different approaches to quantum gravity take different views on what these microstates are. In string theory, they might be different configurations of strings and branes. In loop quantum gravity, they might be different ways of connecting quantum loops. But the fact that entropy scales with area rather than volume tells us something deep about the structure of space itself. It hints that reality might be holographic in a sense, that three-dimensional space might emerge from two-dimensional quantum information somehow, that the world we experience, with its depth and volume and seeming continuity, might be built from something more fundamental, something discrete and surface-like that we haven't directly observed, but which manifests in the properties of black holes. It's a clue from nature, written in the language of thermodynamics and information theory, suggesting that space is not what it appears to be at the deepest level. The holographic principle suggests that all the information in a volume of space can be encoded on its boundary. Taking the idea from black hole entropy further, the holographic principle proposes something radical: that everything happening in a three-dimensional region of space can be completely described by information encoded on the two-dimensional boundary of that region. It's called holographic by analogy to optical holograms, where a two-dimensional surface encodes three-dimensional information. But the holographic principle is deeper. It's not just that you could represent three-dimensional information on a surface, but that the surface description might be more fundamental, with the three-dimensional space being an emergent or derived concept. If true, this means that the universe might have one fewer dimension than we think at the fundamental level. What we experience as a three-dimensional universe with time might actually be encoded on a two-dimensional surface, with the interior volume being a kind of projection or hologram of that surface information. This is still speculative, still being worked out mathematically, but it has been rigorously developed in certain contexts particularly in the ADS-CFT correspondence, a mathematical relationship between gravity in certain curved spacetimes and quantum field theories on their boundaries. The principle suggests that information, not matter or energy or even spacetime itself, might be the most fundamental currency of reality. That the universe is, at its deepest level, an information processing system, with all the richness and complexity we observe emerging from the relationships and transformations of that information. It's a profound shift in perspective, one that physicists are still exploring, still trying to understand. Black holes led us here to questioning the very nature of dimensions and the structure of reality itself. We still don't have a complete quantum theory of gravity that fully describes black hole interiors. Despite all we've learned, despite the beautiful mathematics of general relativity and the successful predictions of quantum mechanics, we still don't have a complete theory that successfully merges the two. We don't have quantum gravity, not in a finalized, tested, verified form. This means we can't definitively answer what happens at the singularity, whether information is truly preserved, how exactly Hawking radiation carries information out, what the microstructure of space-time is, or what conditions were like at the Big Bang. These questions all require quantum gravity to answer properly, and we're not there yet. Several candidate theories exist: string theory, loop quantum gravity, causal set theory, and others, each with its own strengths and challenges. But none has been experimentally confirmed. We don't have the technology to probe the Planck scale directly, and we can't observe the interior of black holes where quantum gravity effects would be strongest. So we work with what we have: mathematical consistency, indirect evidence, theoretical constraints. We develop these theories, work out their predictions, look for places where they might differ from standard physics in ways we could potentially observe. We wait for experiments and observations that might favor one approach over another. In a way, this is exciting. It means we're living in a time when fundamental physics is still being discovered, when the deepest questions are still open, when the story isn't finished. Black holes mark the boundary of current knowledge, the places where our best theories reach their limits and admit they don't know everything. And that means there's still mystery, still room for discovery, still possibilities that tomorrow's physicists might reveal that would surprise us today. Black holes might be connected through wormholes, Einstein-Rosen bridges that link distant points in space-time. When Schwarzschild found his solution to Einstein's equations, there was a strange feature hidden in the mathematics. The space-time didn't just describe the exterior of a black hole and a singularity. It also contained a mirror region, another asymptotically flat space on the other side of the singularity, connected by what's called an Einstein-Rosen bridge or wormhole. In the simplest case, this bridge connects two different regions of the same universe, or possibly two different universes. Matter falling in from one side would hit the singularity, but hypothetically could emerge from the white hole end in the other region. Though the mathematics shows this probably doesn't work in practice due to instabilities. More realistically, modern research suggests that quantum entanglement and wormholes might be related. The ER-EPR conjecture proposes that when two particles are entangled, connected through quantum correlations, they might also be connected by a tiny wormhole at the Planck scale. Einstein-Rosen bridges, ER, might be the same as Einstein-Podolsky-Rosen entanglement, EPR. If true, this would mean that wormholes aren't just features of exotic spacetimes, but are ubiquitous, existing wherever quantum entanglement exists, which is essentially everywhere. Every entangled pair of particles might be connected by microscopic wormholes, too small to traverse but existing nonetheless. These wormholes wouldn't allow faster-than-light communication or travel. Quantum entanglement doesn't allow that either. But they might represent a deep connection between the geometry of space-time and the quantum correlations that permeate reality, showing that gravity and quantum mechanics are more intimately related than we realized. It's speculative, mathematically sophisticated, and still being worked out. But it suggests that black holes, wormholes, and quantum entanglement might all be different aspects of the same underlying physics. The ER-EPR conjecture proposes that quantum entanglement and wormholes might be the same phenomenon. Let's linger on this idea for a moment, because it's one of the most intriguing recent developments in theoretical physics. Quantum entanglement has always seemed mysterious. Two particles can be correlated in ways that seem to involve instantaneous influence across any distance, what Einstein called spooky action at a distance. But what if that connection isn't just abstract, but geometric? What if entangled particles are literally connected by a tiny wormhole threading through space-time, a quantum tunnel linking them regardless of how far apart they are in ordinary space? This wouldn't allow faster-than-light signaling. Just as you can't send messages through quantum entanglement, you couldn't send messages through these microscopic wormholes. But it would mean that space-time connectivity and quantum correlations are the same thing, that geometry emerges from entanglement, or perhaps that both emerge from something even more fundamental. Some physicists are exploring whether space-time itself might be built from entanglement, whether the fabric of reality is woven from quantum correlations, with distance and geometry being derived concepts rather than fundamental ones. It's called space-time from entanglement, and it's a radical reimagining of what space and time are. If this is right, black holes become even more interesting. The entanglement structure around and inside a black hole might determine its geometry, its properties, even its eventual fate. The information paradox might be resolved by understanding how entanglement is distributed and preserved. We're far from confirming any of this, but it represents physics at its most adventurous, connecting dots between seemingly separate phenomena, looking for deep principles that unify our understanding, willing to reconsider everything if that's what the evidence demands. Next-generation gravitational wave detectors will observe black hole mergers throughout the entire universe. We're living in the early days of gravitational wave astronomy. LIGO and Virgo have opened a new window on the universe, but they're just the beginning. Next-generation detectors are being planned and built. Instruments like Einstein Telescope in Europe, Cosmic Explorer in the United States, and others around the world. These future observatories will be far more sensitive than current detectors. They'll be able to hear black hole mergers from the very edge of the observable universe, from times when the cosmos was young and stars were just beginning to form. They'll detect not just dozens of mergers per year, but potentially thousands, building a complete census of black hole populations across cosmic history. With that much data, we'll be able to answer questions that are currently speculation. How do black holes form in the early universe? How do their properties evolve over time? Are there populations of black holes we haven't discovered yet? Do the properties of black holes reveal anything about the formation of the first stars, the first galaxies? We'll also be able to test general relativity more precisely. Every merger is a test of Einstein's equations in the most extreme conditions. We can look for deviations, for hints that gravity behaves differently than predicted, for evidence of new physics lurking in the strongest gravitational fields. The future of black hole astronomy is bright, or perhaps more accurately, loud. We'll be listening to the universe in ways we've only just begun to explore, hearing stories written in the vibrations of space-time itself, learning about cosmic history from the echoes of collisions that happened billions of years ago. The Laser Interferometer Space Antenna, planned for the 2030s, will detect supermassive black hole mergers. LIGO and Virgo are ground-based detectors, and they're sensitive to higher frequency gravitational waves, the kind produced by stellar mass black holes merging. But supermassive black hole mergers produce lower frequency waves, below what ground-based detectors can sense. The Earth itself vibrates too much, creating noise that masks these lower frequencies. The solution is to go to space. LISA, the Laser Interferometer Space Antenna, is a planned space-based gravitational wave observatory. It will consist of 3 spacecraft flying in a triangular formation, separated by 2.5 million kilometers, using lasers to precisely measure the distances between them. LISA will be able to detect supermassive black hole mergers anywhere in the universe. When 2 galaxies merge and their central black holes eventually spiral together, LISA will hear it. Not just the final merger, but potentially years of the inspiral leading up to it. We'll be able to watch the process unfold, to see how supermassive black holes find each other and merge, to study the dynamics in real time. These observations will tell us about galaxy evolution, about how supermassive black holes grow, about the history of cosmic structure formation. They might even detect intermediate mass black hole mergers, filling in that missing population, or primordial black hole mergers from the early universe. Launch is planned for the 2030s, a little over a decade away. By the time LISA is operational, we'll have an entire spectrum of gravitational wave observatories, ground-based detectors for stellar mass mergers, LISA for supermassive ones, potentially pulsar timing arrays sensitive to even lower frequencies. The universe's gravitational wave symphony, played across all frequencies, finally audible to us. Future telescopes may be able to test whether the region inside the event horizon matches theoretical predictions. The Event Horizon Telescope showed us the shadow of black holes, the silhouette against the bright accretion disk. But future observations might go further, actually testing the space-time geometry near and even inside the event horizon in indirect ways. One possibility is observing the photon ring structure more carefully. Light can orbit a black hole multiple times before escaping, creating nested rings in the image. These rings encode information about the space-time geometry, about whether the black hole's properties match general relativity's predictions or show deviations. Another approach is studying echoes in gravitational wave signals. When black holes merge, the ring-down phase might contain subtle echoes. reflections of gravitational waves from structures near the horizon. If the horizon isn't quite what general relativity predicts, detecting these echoes would be evidence of modifications to black hole structure, of quantum effects manifesting in observable ways. We might also study the orbits of stars or gas clouds very close to black holes, looking for precession or other effects that reveal the space-time structure. The closer we can observe to the horizon, the more precisely we can test whether black holes behave exactly as predicted, or whether there are surprises. None of these observations could tell us what's inside the event horizon directly. That's still hidden from us. But they could test whether the event horizon exists as described, whether the exterior space-time matches expectations, and potentially reveal hints of quantum gravity effects that modify the classical picture. Every improvement in observational capability brings us closer to testing our theories at their limits, to finding either confirmation or the deviations that would point toward new physics. Astronomers are searching for the first light black holes formed in the early universe. Somewhere in the distant universe, hidden in the earliest epochs of cosmic history, are the first black holes. Maybe they formed from the first generation of stars, population 3 stars, massive objects made from pristine hydrogen and helium, burning hot and fast and collapsing at the end of their brief lives. Or maybe they formed through direct collapse of gas clouds, as we discussed earlier. Finding these first black holes would tell us about the conditions in the early universe, about how structure began to form, about the transition from the smooth, nearly uniform state after the Big Bang to the rich complexity we see today. Their fossil records, preserved in the depths of space and time. The James Webb Space Telescope is already searching for signs of these early black holes, looking at the most distant quasars, studying galaxies from when the universe was only a few 100 million years old, trying to understand how supermassive black holes could already exist so early. Future telescopes, even more powerful, will push back further in time, looking for the signatures of black hole formation in the first 100 million years after the Big Bang. They'll study how these first black holes affected their surroundings, ionizing gas, influencing star formation, seeding the growth of galaxies. Every discovery pushes back our chronology, showing us earlier and earlier moments in cosmic history. And somewhere in that history is the story of the first black holes, the pioneers that paved the way for all the black holes we see today. Finding them, studying them, understanding them would complete another chapter in our understanding of how the universe evolved from simple to complex. The population of stellar mass black holes in our galaxy is largely unknown and unmapped. For all our progress, we've only confirmed a few dozen stellar mass black holes in the Milky Way. But there should be millions, maybe tens of millions, scattered throughout the galaxy. Most are invisible to us, isolated and dark, revealed only when they happen to pass near something we can observe. Future surveys aim to change this. Gravitational microlensing searches, monitoring millions of stars for the brief brightening events that occur when a black hole passes in front of them, could discover isolated black holes by the hundreds or thousands. Gravitational wave detectors, as they improve in sensitivity, will catch more and more mergers, revealing black holes that were previously unknown. We'll build maps showing where black holes are concentrated, in the galactic plane, in the bulge, in the disk. We'll measure their mass distribution, learning which masses are common and which are rare. We'll track their motions, understanding how they move through the galaxy over cosmic time. This census matters because black holes are part of the galaxy's ecology. They represent the endpoints of massive stellar evolution, the remnants of the biggest stars. Understanding their population tells us about the star formation history, about supernova rates, about the chemical enrichment of the galaxy over billions of years. And occasionally, one of these invisible wanderers might pass near our solar system, close on cosmic scales, though still many light years away. Not close enough to be dangerous, but close enough to study in detail, to measure precisely, to learn from in ways that distant black holes don't allow. Every invisible object we make visible adds to the story. Scientists are exploring whether black holes could theoretically be used for energy extraction via the Penrose process. Roger Penrose discovered something remarkable. In principle, you could extract energy from a rotating black hole. It's called the Penrose process, and it works through the ergosphere, that region where space itself is dragged around the black hole. The idea is this: you send an object into the ergosphere on a carefully chosen trajectory. Inside the ergosphere, you split the object into two pieces in just the right way. One piece falls into the black hole, but it has negative energy relative to the outside universe. Strange, but allowed in the ergosphere. The other piece escapes with more energy than the original object had. You've extracted energy from the black hole's rotation. The black hole spins a little slower afterward, having given up some of its rotational energy to the escaping particle. In principle, you could repeat this process until the black hole stops rotating entirely, extracting all its rotational energy in the process. An advanced civilization, Kardashev Type 2 or higher, might theoretically use this to power themselves, building infrastructure around rotating black holes and harvesting their spin energy. It's pure speculation, of course, far beyond anything we could attempt. But it shows that black holes aren't just cosmic destroyers. They're also potential energy resources, if you're sufficiently advanced and ambitious. There are other proposals too, the Blandford-Znajek process, which might extract energy through magnetic fields threading the black hole, or superradiance, where waves can amplify themselves by bouncing off the ergosphere. Black holes, paradoxically, might be sources of power rather than just sinks of matter. We're nowhere near attempting this, and we might never be. But it's a reminder that physics allows possibilities beyond what we've actualized, that the universe contains potential we've barely begun to explore. The study of black holes has revealed deep connections between gravity, quantum mechanics, information theory, and thermodynamics. Perhaps the most profound contribution of black hole physics isn't any single discovery, but the way it has shown how different areas of physics are connected. Gravity and quantum mechanics, usually thought of as separate domains, meet at black hole horizons. Thermodynamics and information theory, concepts developed for steam engines and communication systems, turn out to describe the fundamental properties of space-time itself. Black holes have entropy, temperature, and obey laws that mirror thermodynamics. Information theory became crucial to understanding the information paradox. Quantum entanglement might be related to space-time geometry through wormholes. The holographic principle suggests that dimensionality itself is negotiable, that surfaces and volumes are interchangeable. These connections hint at something deeper, some unified framework that we haven't fully articulated yet. They suggest that concepts we developed separately, gravity, quantum mechanics, information, entropy, are actually different facets of a single underlying reality, different ways of describing the same fundamental structure. Black holes have been teachers in this respect, forcing us to think about these connections, to recognize that the boundaries between different areas of physics are more permeable than we thought. Every paradox, every puzzle, every strange prediction has pushed us to reconsider our assumptions, to look for deeper principles. The final theory of quantum gravity, when we find it, will probably show how all these threads weave together. And black holes will have been the Rosetta Stone, the key that helped us decode the language of reality at its most fundamental level. Every question we answer about black holes seems to raise new ones, pushing the boundaries of human knowledge. When black holes were first discovered mathematically, they raised the question, do they actually exist? Observations answered yes, but raised new questions. How do they form? How common are they? What properties do they have? When we detected black holes, we asked, can we image them? The Event Horizon Telescope said yes, but raised new questions. What's the structure of the photon ring? What causes the asymmetries? What can we learn from multiple wavelengths? When we discovered Hawking radiation theoretically, we asked, does information escape? The information paradox remains unsolved, spawning questions about holography, complementarity, firewalls, the nature of quantum entanglement. This pattern repeats endlessly. Every answer opens new avenues of inquiry. Every solved mystery reveals deeper mysteries. It's frustrating sometimes, but also exhilarating. It means we're not running out of questions, not approaching some final theory where everything is known and nothing remains to discover. Black holes ensure that physics stays alive, stays interesting, stays full of wonder. They sit at the intersection of our best theories and mock our attempts at complete understanding. They're patient teachers, revealing their secrets slowly, one discovery at a time, always holding something back for the next generation to uncover. Perhaps we'll never fully understand them. Perhaps there will always be another layer, another question, another mystery waiting beneath the surface. And maybe that's how it should be. Some objects, some phenomena, resistant to complete comprehension, keeping us humble and curious, and always reaching for deeper understanding. Black holes remind us that the universe operates on principles that transcend everyday intuition. We evolved in a world of moderate speeds, weak gravity, large scales where quantum effects are hidden and space-time is flat. Our intuitions developed in that environment, shaped by experiences that never included anything like a black hole. So when black holes tell us that time can slow down, that space can curve back on itself, that information might be paradoxical, that singularities might exist where physics breaks down, these ideas feel alien, counterintuitive, almost impossible. But the universe doesn't care about our intuitions. It operates according to principles that are deeper, stranger, more beautiful than anything we could have imagined from everyday experience. Black holes are ambassadors from that deeper reality, showing us that the cosmos is far richer than the slice we experience directly. Learning to think about black holes requires us to think mathematically, abstractly, to trust the equations even when they lead to conclusions that feel wrong. It requires intellectual humility, the willingness to admit that our instincts might mislead us, that reality owes us nothing in terms of being easily comprehensible, and yet we can understand them, at least partially, not through intuition, but through reason, mathematics, observation, careful thought. We can extend our minds beyond their ordinary reach, grasp concepts that don't correspond to anything in daily life, and build understanding despite the strangeness. Black holes teach us that the universe is knowable, even when it's not intuitive, that human minds can comprehend even what we can't directly experience. It's a profound validation of science as a way of knowing, of mathematics as a language of nature, of our capacity to understand despite our limitations. Despite decades of study, black holes still inspire wonder and challenge our understanding of reality itself. We've come a long way together tonight. 100 facts about black holes, from their naming to their nature, from their formation to their ultimate fate, from observational confirmations to theoretical speculations. We've explored event horizons and singularities, gravitational waves and Hawking radiation, information paradoxes and holographic principles, and yet, after all of that, black holes remain fundamentally mysterious. We understand them better than ever before, but they still resist complete comprehension. They still pose questions we can't fully answer, still suggest possibilities we can't fully articulate, still point toward physics we don't yet have. There's something appropriate about that. Black holes are, by definition, objects whose interiors we can never observe, whose singularities we can never probe, whose final secrets might always remain hidden behind event horizons. They're cosmic mysteries made manifest, darkness made physical, the unknown given a precise mathematical description but never completely unveiled. And they're beautiful in their way. Not in any visual sense, though the images we've captured are stunning, but in the mathematical elegance of their description, in the deep physical principles they embody, in the questions they raise about the nature of space, time, information, and reality. Black holes stand at the center of some of the deepest questions we can ask. What is space? What is time? What happens to information? Does the universe have limits? Can physics describe everything, or are there boundaries beyond which knowledge cannot pass? They remind us that we live in a universe stranger and more wonderful than we typically imagine, a cosmos that contains not just stars and planets, but also these impossible objects, these tears in space-time, these monuments to gravity's ultimate power. And so we come to the end of our journey through the darkness and the mystery, through 100 facts about objects that represent both the limit of our knowledge and the frontier of our understanding. Perhaps you're still awake, thinking about these ideas, contemplating the strangeness of a universe that contains black holes. Or perhaps you drifted off somewhere along the way, fact 37 or 62 or 89, sliding into sleep while space-time curved and singularities beckoned in your dreams. Either way is perfect. That's what this was for. Black holes teach us many things, but perhaps the most important lesson is this. The universe is larger, stranger, and more beautiful than we can fully grasp, and yet we can still reach toward understanding. We can still ask questions, build theories, make observations, learn. We can still wonder. Tomorrow, or whenever you wake, the black holes will still be out there, at the center of our galaxy, scattered throughout the cosmos, merging in distant space, slowly evaporating through quantum effects, existing at the boundary between what we know and what we're still learning. And we'll still be here, looking up, asking questions, pushing the boundaries of understanding a little further, one discovery at a time. Thank you for joining me on this journey. Sleep well, dream peacefully, and know that the universe, in all its darkness and light, all its mystery and wonder, will be waiting when you return. Good night.